1. Jupiter has permanent auroras. Jupiter continuously displays powerful auroras that remain active, located at its magnetic poles. Unlike Earth, where auroras are occasional events, Jupiter's auroras are constant. This happens because the source of energetic particles is not the Sun, but the Moon. Io. Io's volcanic eruptions release vast amounts of ionized material, which directly fuels the auroras, keeping them visible at all times. Io and Jupiter are connected by an electromagnetic circuit created by the planet's magnetic field. As Io orbits, its interaction with Jupiter's magnetic field generates intense currents. These currents, called Birkeland currents, channel energy straight to the poles, where they collide with the upper atmosphere, exciting atoms and producing light. The result is a perpetual aurora powered by a volcanic moon. Jupiter's magnetic field is the largest and strongest of all planets in the solar system, extending for millions of kilometers. This creates a vast magnetosphere that houses several moons. This system functions like a natural reactor, trapping particles and directing them toward the poles. Jupiter's fast rotation, completing one full spin every 10 hours, enhances this process. The entire system operates in a dynamic, efficient, and energetically active way. Missions like Galileo, Cassini, and Juno have observed Jupiter's auroras in detail, capturing not only visible light but also X-ray and ultraviolet emissions. These signals reveal that the aurora is deep and layered with areas of varying energy levels. The brightness fluctuates but never fully fades away, confirming that Jupiter's system has well-established internal energy sources. The auroras appear not just as fixed arcs, but also in the form of belts and pulsating spots. Occasionally they form spirals or orbital patterns synchronized with the moons, suggesting that other moons besides Io influence the phenomenon. For example, Europa might cause small brightness fluctuations. This behavior makes Jupiter's auroras a system that responds to orbital dynamics. Jupiter's internal heat also helps maintain high magnetic activity. The planet emits more energy than it receives from the Sun, thanks to the slow contraction of its core. This heat sustains convection within its metallic interior and the generation of its magnetic field. This energy self-sufficiency is unusual among planets and keeps the auroral system stable, even in the absence of external disruptions. The plasma originating from Io forms a torus around the planet, concentrated near the equatorial plane. This torus carries sulfur and oxygen ions and acts as a reservoir of charged particles. Some of this plasma is directed toward the polar regions by tilted magnetic lines, completing the feedback loop of the auroras. Every component of the system contributes to its long-term sustainability. Beyond their visual beauty, the auroras provide insight into magnetospheric physics. They offer a means to study particle acceleration, energy conduction, and interactions between celestial bodies. The processes observed on Jupiter have similarities to those seen in pulsars and magnetized exoplanets, broadening the scope of the data beyond our solar system. Jupiter serves as a model for energetic atmospheres on a planetary scale. The persistent auroras also impact Jupiter's upper atmosphere. They heat high-altitude regions, creating thermal and dynamic effects that are not fully understood. This might affect heat transfer and chemical composition at altitude. Investigating these effects helps us understand atmospheres without a solid surface, further highlighting the complexity of gas giants. This continuous light phenomenon is driven by one of Jupiter's main forces, Io. The hyperactive moon injects the plasma that keeps the system glowing. In the following section, we'll explore how Io's activity shapes the space surrounding Jupiter. The link between magnetism, moon, and aurora is an extreme example of planetary interdependence. Jupiter's innermost large moon, Io, is a hyperactive volcanic body. With over 400 active volcanoes, Io's surface is constantly changing. The heat fueling these eruptions comes from internal friction caused by tidal forces. Jupiter and the nearby moons stretch and deform Io with each orbit, converting orbital energy into internal heat. Every 42 hours, Io completes one orbit around Jupiter, experiencing intense shape changes. This cycle of compression and expansion heats the moon's interior, keeping its mantle partially molten. The phenomenon is sustained by a resonance with Europa and Ganymede, which maintain Io's slightly elliptical orbit. This small eccentricity is enough to keep the internal temperature high, resulting in a boiling crust. Volcanic plumes shoot gases and particles up to 400 kilometers high. These materials escape Io's weak gravity and spread across Jupiter's environment, creating a plasma torus that feeds Jupiter's magnetic field and auroras. Io's surface is covered in sulfur in various chemical forms, giving it unique yellow, red, and orange hues. Lava lakes occupy vast areas with many still active. Plains of solidified lava and erupting volcanoes make up an ever-changing landscape. Impact craters are rare as the surface is constantly renewed. Unlike Earth, Io lacks tectonic plates. Its volcanic activity is localized, driven by shallow magma chambers. There is no erosion, rivers, or significant atmosphere. The lack of air prevents heat from escaping at the surface, keeping the environment extremely dynamic and hostile. The plumes from Io's volcanoes are mainly made of sulfur dioxide, which freezes as it falls back to the surface, forming deposits around the eruption sites. Some plumes also contain rock particles and simple organic compounds. This material interacts with the space environment, creating electromagnetic phenomena around the Moon. Io is an active source of material and energy. The radiation surrounding Io is extremely intense due to its proximity to Jupiter's magnetic field, posing a challenge for probes and measurement instruments. Any prolonged mission to the Moon requires special shielding and limited exposure time. Nevertheless, missions like Galileo and Juno have captured valuable images and data. New missions are being planned for dedicated flybys. Io's continuous activity demonstrates that even small moons can be geologically complex. Unlike Earth's moon, which is inert, Io is energetically connected to its planet. This activity not only affects the Moon, but also the surrounding system. It's a constant interaction between gravity, heat, magnetism, and plasma. Models suggest Io may have a layer of liquid magma beneath its crust, explaining the frequency and intensity of its eruptions. Studying this could help us understand how rocky worlds behave under intense gravitational forces. It's a form of geodynamics that doesn't rely on internal radioactivity, like Earth's. Io exemplifies how external forces can keep a celestial body active for billions of years. Its connection to Jupiter transforms orbital motion into heat and eruptions, offering insights into volcanism on exoplanets and distant moons. Saturn's atmosphere consists of dense cloud layers that become progressively thicker toward the interior. Any object attempting to descend would be crushed by the pressure before reaching anything solid. This makes direct measurements exceedingly difficult. As a result, missions must operate from orbits or flybys. Saturn's iconic rings don't significantly contribute to its mass. They are primarily made of ice and rock in small particles. Although visually spectacular, their total mass represents less than 0.01% of the planet's total mass. Despite this, they affect the distribution of light and the thermal balance around the planet, contributing to the perception of Saturn's lightness. Saturn's lightness offers insight into its origin and evolution. It formed in the cold regions of the solar system where hydrogen and helium were abundant. These gases quickly accumulated around a small initial core. As a result, Saturn has great volume but lacks significant compactness. Its rapid formation allowed it to capture the lightest elements before they dissipated. Other gas giants such as Jupiter, Uranus, and Neptune are denser. Jupiter has stronger gravity and extreme internal pressures which compress its materials. Uranus and Neptune, on the other hand, contain more ice and heavier compounds, which increase their density. Saturn is notable as a large yet light planet, making it unique among its class. The idea of a planet that could float on water helps visualize its composition. Although it is a theoretical comparison, it is scientifically accurate. Density is an important parameter in astrophysics used to infer a planet's internal structure. In Saturn's case, this indicates a predominance of gases and a lack of dense materials in large quantities. This analysis supports models of Saturn's formation and composition. Saturn's lightness contrasts with its gravitational power, which is still strong enough to retain numerous moons and an extensive ring system. This apparent contradiction highlights the significance of mass distribution. The next section continues to explore atmospheric behaviour in gas giants, focusing on Jupiter and its long-lasting storms. Jupiter boasts enormous storms that can last for centuries, like the Great Red Spot. Jupiter's Great Red Spot is an immense storm that has persisted for at least 350 years. It is an anti-cyclonic system, meaning its winds rotate opposite to a cyclone. Located in Jupiter's southern hemisphere, it has been visible since the earliest telescopes. With a diameter larger than Earth's, it holds the title of the largest known atmospheric storm. Its longevity challenges meteorological models. While Earth's storms last days or weeks, the Great Red Spot has lasted for centuries. This is because Jupiter lacks a solid surface to dissipate energy. Additionally, the planet emits internal heat that fuels its atmospheric systems. This heat is generated by gravitational compression, which keeps convection active. The storm is sustained by a constant internal energy source. The spot is positioned between two opposing jet streams, which confine it. These bands prevent the storm from moving significantly north or south, creating an atmospheric cradle that maintains its rotation. This results in an unusual level of stability for such a weather phenomenon. However, the spot has been shrinking in size over recent decades. The storm's structure is deep. Data from the Juno mission suggests it may extend hundreds of kilometers below the visible clouds. This makes it more similar to a convective column than a surface-level storm. Its depth helps conserve angular momentum and thermal energy, which are key to its exceptional longevity. The chemical composition of Jupiter's atmosphere includes ammonia, ammonium sulfide, hydrogen, and helium. Chemical interactions between these compounds, combined with solar radiation, might explain the reddish colour of the spot. However, the exact mechanism remains uncertain. The hue changes over time, indicating shifts in cloud altitude or composition, which only add to the intrigue. Other storms emerge and disappear on Jupiter, but the Great Red Spot is the most enduring. Smaller spots, such as Oval Ba, were formed by the merger of three white storms in 2000. These structures demonstrate that Jupiter is prone to long-lasting atmospheric events. Some of them interact with one another, creating mergers, absorptions, and redistributions of energy. Jupiter's atmosphere is highly dynamic. Jupiter's rapid rotation, one full spin in about 10 hours, reinforces the formation of bands and rotating systems, generating strong Coriolis effects that stabilize storms. The bright zones and dark belts on the planet's surface reflect this dynamic structure. The Great Red Spot is integrated into this system, and its position has remained stable for centuries. The Voyager, Galileo, and Juno probes have helped scientists understand this storm better. These missions have gathered images, spectra, and gravitational data, revealing not only the depth of the spot, but also internal speeds and compositions. This data continues to be analysed to build more comprehensive models of atmospheric dynamics. The spot's persistence serves as a reference for studies on planetary weather. Understanding the Great Red Spot helps explore the limits of planetary meteorology. The processes seen on Jupiter inform the study of gaseous exoplanets, many of which display similar long-lasting storms. As a result, Jupiter functions as a natural laboratory for extreme atmospheric phenomena. The storm is a key feature in the study of convection, rotation, and atmospheric stability. Neptune's atmosphere houses the fastest winds in the solar system. Neptune's winds are the fastest ever recorded on any planet, with speeds exceeding 2,100 km per hour in certain areas. These winds are faster than the speed of sound in Earth's air. It's surprising that a planet so far from the Sun can have such a dynamic atmosphere. The energy required to sustain these winds is still under investigation. Neptune receives only about 1/1900th of the solar energy that Earth gets, yet its atmosphere still exhibits bands, storms, and active circulation systems. This suggests that Neptune possesses an internal heat source. It emits 2.6 times more energy than it absorbs from the Sun. This thermal imbalance may explain the strength of the winds. Neptune's atmosphere is made up of hydrogen, helium, and methane. Methane gives the planet its characteristic blue colour by absorbing red light. The upper clouds consist of methane ice crystals, while deeper, denser layers exhibit strong vertical motion. These gradients favour the formation of atmospheric jets, The most intense winds are found in the mid-latitude regions, both north and south. These areas concentrate large amounts of energy into circular patterns and flow lines. Neptune's rapid rotation, completing a full spin every 16 hours, strengthens these winds. The Coriolis force is powerful and organizes the motion into well-defined bands, similar to those seen on Jupiter and Saturn. The Voyager 2 probe and space telescopes helped map Neptune's atmospheric patterns. During Voyager's flyby, the Great Dark Spot was observed, a storm similar to Jupiter's Great Red Spot. Although the Great Dark Spot disappeared years later, similar spots have reappeared, indicating that the winds continue to generate large-scale weather systems. Storms on Neptune can last for weeks or months and are formed by a high-pressure region surrounded by intense rotational winds. Some of these storms display white clouds made of methane ice, making them easier to observe. These systems move rapidly around the planet, reflecting the strength of the winds. However, the exact formation mechanisms are still not fully understood. The contrast between bright and dark regions on Neptune shows intense convective activity. Warmer areas rise while colder regions sink, generating vertical circulation. This convection may be enhanced by the release of internal heat. The combination of thermal gradients and rapid rotation creates powerful winds. It's an extreme atmospheric environment, even when compared to other gas giants. Neptune's internal heat may be a result of the planet's slow contraction, or from other unidentified processes. This heat accumulates and escapes gradually, driving atmospheric convection. Even with extremely low external temperatures, the planet's internal energy is enough to sustain the winds. This supports the idea that planetary meteorology is not solely dependent on sunlight. On Neptune, the heat originates from within. Observations from telescopes like Hubble and James Webb continue to detect new atmospheric structures. Winds change in intensity and direction over the years, revealing climate cycles. This suggests that Neptune's atmosphere is in constant transformation. Monitoring these shifts helps scientists understand how atmospheres behave on cold, distant exoplanets. It offers an opportunity to compare extreme environments in different contexts. Neptune's wind dynamics reinforce the importance of planetary rotation and internal heat. Even in regions receiving little solar energy, the atmosphere can remain active and complex. The planet's supersonic winds challenge traditional meteorological models. Next, we move to the world of gas giants once more with Uranus, the planet that spins on its side. This distinct feature has profound implications for its seasonal behavior. Each hemisphere experiences extended periods of light or darkness. A single solar day on Uranus can span up to 42 Earth years, depending on the season. When one of the poles faces the sun, it enjoys continuous daylight for decades, while the opposite pole remains in darkness for the same length of time. This results in extreme thermal patterns, where regions gain or lose energy over prolonged periods. However, the atmosphere doesn't show the drastic contrast one might expect. Despite these extreme seasons, Uranus's atmosphere appears surprisingly uniform, which perplexes scientists, as the planet should exhibit stark weather patterns. One explanation could be the presence of deep layers of residual heat. Another possibility involves large-scale atmospheric circulation that efficiently redistributes energy. Nevertheless, the exact mechanisms remain under investigation. The planet's sideways rotation also affects its magnetic field. Uranus's magnetic field is tilted in relation to its rotational axis and is offset from its geographic center. This results in complex and asymmetrical magnetic patterns. The resulting magnetosphere is unstable and rotates irregularly around the planet. This behavior is unlike any other known planetary magnetic field. The extreme tilt is likely the result of an ancient collision with a massive object. An impact with a protoplanet might have knocked Uranus onto its side in its early stages. This theory would explain not just the tilt, but also the lack of significant internal heat. Unlike Neptune, Uranus releases almost the same amount of energy as it receives from the Sun, suggesting that some of its heat may have been lost after the collision. Uranus is surrounded by narrow dark rings composed of small, faintly reflective particles. They orbit the planet in the equatorial plane, which is nearly perpendicular to the orbital plane. This means the rings point toward the Sun during Uranus's solstices. The orientation of the rings changes significantly throughout their orbit, affecting their visibility from Earth. At certain times, they nearly disappear from view. Uranus's moon system shares the planet's tilt. The major moons orbit in the same inclined plane, implying they formed after the impact. These moons show diverse terrain, with canyons, plains, and evidence of past geological activity. Miranda, one of the largest moons, has unusual geological formations that suggest intense tectonic activity. The tilt of the planet may have contributed to these formations. Uranus's atmosphere contains hydrogen, helium, and a substantial amount of methane. Methane absorbs red light, giving the planet its blue-green hue. In visible light, Uranus appears relatively inactive, but in infrared, patterns of bands, storms, and thermal variations become evident. This indicates that there are hidden dynamics not visible to the naked eye. Observations from Voyager 2 and various space telescopes have continued to reveal new details. Despite its calm outward appearance, Uranus shows signs of seasonal activity in its upper atmosphere. With the upcoming solstice in 2030, new observations will become possible. This alignment will allow closer study of how the sideways rotation and polar illumination affect the planet. Uranus remains a partially solved mystery. Uranus's sideways motion challenges traditional expectations about planetary formation and evolution. Its unique rotation affects its climate, magnetism, and orbital structure. The next section continues to explore extreme behaviors in gas giants, focusing on Titan, Saturn's moon, which has a dense atmosphere and methane lakes. Neptune emits more heat than it absorbs. Neptune radiates about 2.6 times more energy than it receives from the Sun. This internal heat is surprising given the planet's distance, more than 30 times farther from the Sun than Earth. At such a distance, solar energy is minimal, yet Neptune maintains an active and dynamic atmosphere. This excess energy suggests a powerful internal heat source, although the exact mechanism remains unclear. The internal heat might come from slow gravitational contraction, releasing energy over billions of years. Another possibility is radioactive decay in a rocky core. These processes could sustain deep convection, transferring heat to the upper atmosphere. This internal heat helps explain Neptune's extreme weather patterns. It drives the formation of fast winds, storms, and cloud activity. Neptune's atmosphere exhibits strong vertical motion and temperature gradients. Convection transports energy from the interior to higher layers, sustaining dynamic circulation. The excess heat powers jet streams, cyclones, and long-lived storms. These features are observable even in Neptune's cold upper atmosphere. Despite minimal solar input, the system remains active. Unlike Uranus, Neptune's internal energy sustains its weather phenomena. Voyager 2 and Earth-based telescopes have documented storm systems like the Great Dark Spot. These storms emerge, shift, and disappear, fueled by convection and internal dynamics. Some of them resemble Earth's hurricanes, but they are far larger and faster. Their existence depends on continuous energy from within. Neptune's internal heat also influences its magnetosphere and radiation belts. Variations in heat flow can affect atmospheric conductivity and field interactions. The result is a complex magnetic environment that interacts with the solar wind. The planet's magnetic field is tilted and offset from its center, adding complexity to how internal heat manifests in space. Cloud patterns on Neptune support the idea of an active lower atmosphere. Methane ice clouds and deeper hydrogen clouds form dynamic layers. These clouds move quickly and show changes in brightness over time. Monitoring these features helps trace how energy moves from the interior to the surface. Infrared observations have confirmed temperature differences across latitudes and altitudes. The origin of Neptune's heat is not fully explained by current physical models. One hypothesis suggests delayed cooling due to trapped heat from the planet's formation. Another considers phase changes in materials under high pressure. Exotic ices and fluid dynamics may also play a role. While each explanation offers partial insight, no definitive answer has been found yet. The contrast between Neptune and Uranus is particularly puzzling. Both planets are similar in size, mass, and composition, yet Neptune emits substantial internal heat, while Uranus does not. This difference raises questions about planetary evolution and thermal history. It suggests that small differences during formation can have major long-term consequences. Future missions to Neptune may help clarify this mystery. Direct probes and orbiters could measure heat flow and internal structure more precisely. Improved models of fluid and ice behavior under high pressure will also be valuable. Until then, Neptune remains a fascinating case study in unexplained planetary energy. Its heat continues to drive the fastest winds in the solar system, contributing to broader planetary science. It informs models of ice giants, exoplanets, and atmospheric dynamics. Neptune's case shows that distance from the Sun doesn't always mean dormancy. Internal heat can fuel powerful weather systems even in the coldest regions of the solar system. Uranus emits almost no internal heat. Uranus stands out as one of the coldest planets in the solar system, not because of its distance, but due to its lack of internal heat. Unlike Neptune, Uranus emits almost the same amount of energy as it receives from the Sun, making it thermally inert with little evidence of internal heat escaping. The reason for this low heat output remains uncertain and challenges existing planetary evolution models. Uranus and Neptune are similar in size, mass, and composition, yet they differ significantly in internal energy. Uranus's nearly perfect energy balance suggests it has no active heat source, which implies little or no convection in its interior layers. Without internal heat, atmospheric circulation is weaker and less dynamic. The planet's atmosphere appears relatively calm in visible light. Unlike Neptune's dynamic weather, Uranus shows fewer storms and slower winds. There are bands and seasonal changes, but they are less dramatic. In infrared, faint cloud structures and temperature gradients become visible. These signs point to some minimal internal motion. Several theories have been put forward to explain the missing heat. One suggests that Uranus lost its heat during a massive impact early in its history. Such a collision could have released energy and disrupted internal convection. Another theory proposes that Uranus's internal layers are stratified, meaning that if dense materials settled, heat transfer would be blocked. The extreme axial tilt of Uranus supports the impact theory. The planet rotates on its side with a 98°G inclination, which is highly unusual. This tilt might have resulted from a glancing blow by a large protoplanet. Such a strike could also explain the suppression of internal thermal processes. However, direct evidence remains elusive. Uranus's lack of heat also affects its magnetosphere. The planet's magnetic field is tilted and offset, similar to Neptune's, but without internal convection, its magnetic field might be more irregular. This leads to a complex and asymmetric magnetic environment, with its variability complicating interpretation and modelling. The cold interior also impacts atmospheric chemistry and cloud formation. With less internal energy, fewer upward currents carry compounds into higher layers, affecting the composition and layering of clouds. Methane remains the primary absorber of sunlight, giving Uranus its pale blue-green colour. However, the cloud structures are more stable and less reactive. The planet's rings and moons reflect this thermal passivity. The ring system is dark and narrow with little evidence of dynamic interactions. Most of Uranus's major moons show signs of ancient geological activity, but there is little indication of recent surface renewal. This contrasts with the more active satellites of Neptune and Jupiter. Future missions could reveal whether Uranus truly lacks heat, or if current models are overlooking hidden processes. Direct measurements of internal structure and temperature would be crucial. Improved understanding of ice and fluid physics under pressure could offer new insights. Until then, Uranus remains a cold and quiet world with unresolved mysteries. The contrast between Uranus and Neptune remains one of the most puzzling thermal questions in planetary science. Two planets of similar size, mass, and composition, yet one radiates energy while the other is nearly inactive. Studying both is essential for understanding how planets evolve, lose heat, or retain it. Uranus shows that planetary behavior is not always symmetrical, even among seemingly similar worlds. Jupiter acts as a shield for Earth. Jupiter plays a crucial protective role in the solar system due to its enormous gravity. It attracts or deflects many comets and asteroids that might otherwise collide with the inner planets. Acting as a cosmic shield, Jupiter reduces the frequency of potentially catastrophic impacts on Earth. Its position near the asteroid belt makes it particularly effective. This influence has shaped Earth's history of life. The planet's gravitational pull reaches across vast stretches of the solar system, perturbing the orbits of small bodies, capturing, ejecting, or redirecting them. Many comets are deflected into new orbits or expelled entirely. Others are drawn into Jupiter, where they disintegrate. This process limits the number of objects that reach the inner solar system. A famous example is Comet Shoemaker-Levy 9. In 1994, Jupiter captured the comet, pulling it apart with its gravity. The comet's fragments collided with the planet in a series of massive explosions, offering a visual demonstration of Jupiter's shielding effect. Without Jupiter, such objects might have a higher chance of impacting Earth. This event confirmed Jupiter's protective role. Though Jupiter's influence is not absolute, it alters the statistical likelihood of impacts. Models suggest that without Jupiter, Earth would experience more frequent large-scale collisions. However, in certain scenarios, Jupiter can also redirect objects inward. Despite this, its overall effect remains protective in the long run. Its presence helps stabilize the dynamics of the inner solar system. Jupiter also maintains gaps in the asteroid belt known as Kirkwood gaps. These regions are cleared by Jupiter's resonant gravitational interactions. Asteroids in these zones are pushed into new orbits or ejected, reducing the number of Earth-crossing asteroids. Jupiter's gravity shapes entire orbital regions, not just individual objects. Trojan asteroids orbit ahead of and behind Jupiter at stable Lagrange points. These objects are caught in gravitational equilibrium and pose little threat to other planets. Their stability further underscores how Jupiter regulates space debris. The planet serves as both a collector and redistributor of material. Its mass controls much of the small body traffic in the outer solar system. Even in the early solar system, Jupiter likely influenced planetary development. Its inward and outward migration helped shape the structure of the protoplanetary disk. This movement may have prevented a super-Earth from forming close to the Sun. It also contributed to delivering icy material to the inner planets. Jupiter's mass and motion played a key role in sculpting planetary architecture. Jupiter's protective role is one reason it's frequently studied in astrobiology. Its presence could increase the chances of long-term habitability in planetary systems. If giant planets like Jupiter are common, they might make life more stable elsewhere. Observing exoplanet systems helps test this hypothesis. The presence of giant planets could indicate safer zones for Earth-like worlds. The balance Jupiter provides is not fixed but evolves with time. As asteroid orbits shift and comet reservoirs move, Jupiter's role also changes. Long-term simulations track how it moderates risks to Earth. These models incorporate gravitational and body dynamics. Jupiter remains a central force in the solar system's stability. Understanding Jupiter's influence deepens our understanding of planetary defense and system dynamics. Its gravity shapes trajectories, clears paths, and blocks potential threats. While not impenetrable, its shielding effect is significant. As we explore planetary systems beyond our own, Jupiter-like giants may prove essential for planetary safety. The next section shifts focus to another fascinating body, Enceladus, Saturn's icy reflector. Enceladus, one of Saturn's mid-sized moons, is one of the brightest objects in the solar system. Its surface reflects almost all the sunlight it receives, with an albedo close to 1.0. This high reflectivity is due to freshwater ice covering the surface. Continuous resurfacing keeps it clean and bright, with Enceladus appearing nearly white in space imagery. The ice is constantly replenished by geysers erupting from the moon's south pole. These plumes release water vapor and icy particles into space. The material settles back onto the surface, creating a fresh reflective layer. Some particles even contribute to Saturn's E-ring. This process keeps Enceladus pristine and unusually bright. Enceladus's reflective surface allows it to remain relatively cool. Sunlight is not absorbed, but is instead reflected back into space. Despite its small size, the moon stands out in telescope images. The contrast between it and Saturn's darker moons is striking. Its brightness also aids in studying surface composition through spectroscopy. The internal activity that drives the geysers is linked to tidal heating. Saturn's gravity stretches Enceladus, generating heat in its interior. This keeps subsurface water in a liquid state. Cracks near the South Pole, known as tiger stripes, vent this liquid as vapor and ice. This results in both resurfacing and reflectivity. The existence of liquid water beneath Enceladus's icy shell has sparked interest in astrobiology. The subsurface ocean could harbour microbial life. The geysers allow us to sample the ocean indirectly. Spacecraft like Cassini have flown through the plumes, detecting organic molecules and salts consistent with ocean chemistry. Enceladus's bright appearance is thus tied to active geological processes. It is not merely a passive reflector, but a dynamic moon. The high albedo is a sign of ongoing resurfacing, which contrasts with older icy bodies that appear darker and more cratered. Enceladus's youthfulness is evident in its shine. The combination of reflectivity and activity makes Enceladus a top target for future missions. Its surface can be imaged in detail because of its brightness. Flybys and potential landers could study the plumes directly, analysing particles and searching for biosignatures. Its surface is both beautiful and scientifically rich. Unlike many moons, Enceladus defies expectations for small icy worlds. It has a global ocean, active geysers, and a constantly renewed surface. These features make it stand out in Saturn's system. Its high albedo is a visible marker of its uniqueness. Few other bodies match its combination of brightness and geological vitality. The reflectivity also influences its thermal behaviour and orbital evolution. A bright surface radiates heat differently, affecting long-term dynamics. This ties surface features to deeper processes. Understanding Enceladus requires integrating surface observations with interior modelling. Its shine is only the beginning of its complexity. As Saturn's icy beacon, Enceladus offers insights into active moons, ocean worlds, and planetary ring systems. Its bright surface tells a story of internal heat, resurfacing, and potential habitability. The moon reflects more than light. It reflects the promise of life beyond Earth. The next topic will continue exploring icy worlds, possibly focusing on Titan or Europa. Jupiter's storms can persist for centuries. The Great Red Spot is a colossal anticyclonic storm on Jupiter, larger than Earth and active for over 350 years. First observed in the 1600s, it remains one of the most iconic features in the solar system. Unlike storms on Earth, which last for days or weeks, this vortex has endured for centuries. Its persistence challenges current atmospheric models. Scientists are still working to explain its long-lasting nature. The storm rotates counterclockwise and is bounded by powerful jet streams to the north and south. These surrounding currents help contain the storm, preventing it from drifting or dissipating. The stable environment within these bands supports long-term rotation. Wind speeds inside the storm reach over 400 km per hour. Despite shrinking in recent decades, it remains highly active. Below the visible clouds, the storm likely extends deep into the atmosphere. Data from NASA's Juno spacecraft revealed gravitational anomalies in the region. These suggest that the Great Red Spot may reach hundreds of kilometers downward. Its depth provides extra energy and momentum, making it more stable than surface-bound systems. The storm's reddish hue remains a mystery. Some theories suggest that ultraviolet radiation from the sun reacts with compounds like ammonia or phosphorus, which may produce the red colour. However, the exact chemistry is still unknown. The colour has changed over time, suggesting chemical variability. Other storms on Jupiter, such as Oval Ba, exhibit similar structures but are less persistent. These systems form through mergers of smaller storms. While dynamic, they rarely match the size or duration of the Great Red Spot. The variety of storm systems offers a glimpse into Jupiter's turbulent weather and provides insights into atmospheric stability. Jupiter emits more heat than it receives from the Sun. This internal heat helps fuel storms and drives atmospheric convection. Unlike Earth, where solar input dominates weather, Jupiter's heat comes mainly from within. This difference supports long-lived storms like the Great Red Spot. The planet's rapid rotation further shapes its jet streams and storm belts. The absence of a solid surface allows storms to rotate freely. On Earth, Friction from terrain weakens cyclones, but Jupiter's gaseous nature allows vortices to persist much longer. The lack of surface drag is a key factor in the storm's endurance, helping to explain why they can last for centuries. The Great Red Spot is gradually shrinking, however. Observations over the past few decades show a decrease in both its width and height. It once measured over 40,000 km across, but now it's closer to 16,000 km. The reasons for this change remain unclear, but it may signal a long-term weakening or transformation. Even if the Great Red Spot disappears, similar systems may emerge. Jupiter's atmosphere is highly active, with new storms forming regularly. The planet's conditions favour the creation of large rotating systems. The legacy of the Great Red Spot will inform the study of future storms and remains a case study in atmospheric endurance. Jupiter's storms demonstrate the power of internal energy and rapid rotation. They offer a glimpse into weather patterns on gas giants and exoplanets. Understanding these storms enhances planetary climate models. As we continue observing, we may uncover new mechanisms behind their longevity. The next topic shifts focus to Saturn, whose iconic rings are slowly disappearing. Saturn's rings, one of the most recognizable features in the solar system, are gradually fading. Data from NASA's Cassini mission revealed that the rings are losing mass. Particles from the rings are falling into Saturn's atmosphere, pulled by gravity. This process, known as ring rain, is slowly eroding the structure. In tens of millions of years, the rings could vanish. The rings are primarily composed of water ice mixed with dust and organic material. They reflect sunlight brightly and extend over 280,000 kilometers in diameter. Despite their vast size, the rings are incredibly thin, often just a few tens of meters thick. They consist of countless individual particles, each orbiting Saturn independently, creating the illusion of a solid structure. The process of ring loss involves several mechanisms. Micrometeorite impacts stir up particles, sending them into Saturn's magnetic field. Solar radiation and plasma interactions also charge the particles, causing them to spiral inward and fall toward the planet. The rate of mass loss is higher than expected, with Cassini measuring up to 10,000 kilojoules per second. The origin of the rings remains debated. Some theories suggest they formed early in Saturn's history, while others propose they are more recent, possibly the result of a destroyed moon or icy body. If the rings are young, their disappearance would align with a short lifespan. This suggests the rings may be a temporary phase in Saturn's evolution, challenging the assumption that planetary features are permanent. Observations show that the ring system is not uniform. The density, composition, and structure vary across different sections. Some parts are more stable, while others are losing mass faster. For example, the B ring is denser and darker than the outer A ring. Understanding these differences helps model how quickly each section will erode and informs theories about ring dynamics. The loss of rings also affects Saturn's atmosphere. As material rains down, it alters atmospheric chemistry. Ions and water molecules from the rings interact with the planet's upper layers, creating glowing bands near the equator. This exchange ties Saturn's rings directly to its meteorology, showing how interconnected a planet and its ring system can be. Cassini's grand finale orbits past between the rings and Saturn, providing detailed measurements of ring mass, composition, and erosion rates. These final maneuvers confirmed that the rings are a temporary feature. The data reshaped our understanding of ring lifespans, and future missions may provide even more precise estimates. Despite their eventual loss, Saturn's rings remain spectacular. Their structure, resonance patterns, and embedded moons continue to captivate scientists. Tiny moonlets sculpt edges and gaps within the rings, demonstrating the complexity of small body dynamics. Even as the rings fade, they remain a rich source of scientific insight. Saturn, without its rings, will look very different. Over time, the planet may resemble a more featureless gas giant. The loss of the rings won't affect its orbit or mass significantly, but it will change the visual identity we associate with the planet. Future observers may only know Saturn as a ringless world. Saturn's rings remind us that planetary features are not static. They form, evolve, and sometimes disappear. They're fading as part of the planet's natural cycle. Understanding this process helps us study other ring systems and transient features. The next topic may focus on planetary reflectivity, light interaction, or icy moons like Tethys or Dione. Uranus and Neptune may have oceans of diamond. Deep within Uranus and Neptune, extreme pressure and temperature conditions could create solid diamonds. The idea is that carbon atoms in methane molecules are compressed into diamond structures. These diamonds could form in the upper mantle and slowly sink, like rain or hail, into deeper layers. The result would be a theoretical diamond ocean beneath the clouds. While this hasn't been directly observed, the physics behind it is plausible. Laboratory experiments have tested these conditions using high-powered lasers and shock compression. Results show that methane can break apart under pressure, and the carbon can bond into diamond-like crystals. Scientists use these findings to model planetary interiors. The possibility of diamond formation is now widely accepted in planetary science. The process likely begins hundreds or thousands of kilometers below the cloud tops. As methane-rich material descends, it encounters rising pressure and heat. These conditions strip away hydrogen, leaving carbon behind. The carbon atoms then bond into crystalline forms. Over time, these diamonds would accumulate and sink deeper. This phenomenon could help explain some of the thermal behavior of these planets. Sinking diamonds would convert gravitational energy into heat, supporting convection in the interior. This heat may also contribute to Neptune's excess heat output. Uranus, on the other hand, shows little internal heat, suggesting differences in diamond transport or formation. The diamond hypothesis reflects the complex chemistry of ice giants. Despite their name, Uranus and Neptune contain little water ice. Instead, they hold methane, ammonia, and other volatiles. These compounds behave differently under pressure than in terrestrial environments. Planetary scientists refer to them as hot ices due to their exotic states. In Neptune, stronger heat output may help sustain vertical movement of carbon. This circulation would continually replenish regions where diamonds are forming. Uranus, lacking this heat, may have more stagnant internal layers. These differences might stem from its formation history or major collisions. The evolution of each planet impacts its current internal processes. The concept of diamond rain adds to the fascination of these distant worlds. While it has been romanticized, it is grounded in thermodynamic and chemical modeling. Such extraordinary weather is unlike anything in the inner solar system. It serves as a reminder that planetary processes vary widely across different environments. Even familiar elements behave differently under extreme pressure. Future missions to Uranus and Neptune may help confirm these predictions. Instruments could detect seismic patterns or gravitational variations linked to the movement of heavy material. Spectroscopy of ejected particles could also provide indirect evidence. Until then, the diamond ocean remains an intriguing possibility. It motivates the continued exploration of ice giant interiors. Understanding this process helps scientists model similar exoplanets. Many Neptune-like exoplanets have been found orbiting distant stars. Knowing their interior chemistry helps us interpret data on density, temperature, and atmospheric conditions. The diamond formation process may be common across the galaxy. In the end, Uranus and Neptune challenge our assumptions about composition and behavior. Their hidden interiors might contain oceans of carbon in crystalline form. These environments push the boundaries of known physics and chemistry. Studying them expands our understanding of what is possible inside planets. The next topic explores Jupiter's vast and expanding family of moons. Jupiter boasts more than 90 known moons, holding the record for the most known moons in the solar system. These include large moons like Ganymede, Callisto, Io, and Europa, as well as dozens of smaller bodies. Many of these moons were discovered in the last 2 decades thanks to improved telescopes. Some are only a few kilometers wide, orbiting in irregular paths around the planet. The largest moons, known as the Galilean moons, were discovered by Galileo in 1610. These moons are massive enough to be considered planetary bodies in their own right. Ganymede, for instance, is even larger than Mercury. These moons have been studied in detail by spacecraft like Voyager, Galileo, and Juno. They showcase a wide range of geologies and potential habitability. Beyond the major moons, Jupiter's outer region contains irregular satellites. These small moons likely originated as captured asteroids or Kuiper belt objects. Their orbits are often retrograde, inclined, or highly eccentric. These traits suggest that they did not form with Jupiter, but were instead pulled in later by the gravitational interactions. The irregular moons often travel in clusters, suggesting they shared an origin. They may have broken off from a single object after a collision. Over time, Jupiter's gravity captured the fragments. The dynamics of these moons offer clues about the planet's gravitational reach. Their capture also reflects the history of the early solar system. Recent discoveries have dramatically increased the moon count. In 2023, a group of 12 new moons was announced, putting Jupiter ahead of Saturn. Some of these moons are just a few kilometers across. Advanced surveys and long-term tracking have allowed astronomers to confirm their orbits. Many of these objects are faint and are difficult to detect. The study of Jupiter's moons provides insights into satellite formation and planetary systems. Moons can form from surrounding material, as regular satellites, or be captured as irregular satellites. Jupiter hosts both types, making it an ideal laboratory. Their diversity highlights the complexity of moon system evolution, mirroring the systems observed around exoplanets. Some moons interact dynamically with Jupiter's magnetic field. For instance, Io contributes plasma to Jupiter's magnetosphere. Europa and Ganymede may influence auroras and charged particle flows. These interactions demonstrate how moons affect their host planet. Jupiter's system is interconnected on both gravitational and electromagnetic levels. Future missions will explore this system in greater detail. NASA's Europa Clipper and ESA's JUICE will study Europa, Ganymede, and Callisto. These missions aim to investigate ocean worlds and potential habitability. They will also observe interactions among moons and between moons and Jupiter. The sheer number of targets enhances the mission's value. Jupiter's status as the solar system's moon-rich planet may continue to evolve. New discoveries are likely in the coming years. Cataloguing and understanding these moons remains an active area of research. Jupiter's expansive moon system offers more than just quantity. It represents diversity and complexity. From volcanic worlds to icy oceans to tiny captured rocks, its moons cover every major category. They offer a window into planetary formation and dynamics. The next topic may focus on one such icy world, Europa or Ganymede. Neptune has a mutant dark spot. Neptune's Great Dark Spot is a high-pressure atmospheric storm similar in appearance to Jupiter's Great Red Spot. However, unlike Jupiter's storm, it is not permanent. Since its discovery by Voyager 2 in 1999, it has been observed forming, disappearing and reappearing at different latitudes. These changes occur over a few years, indicating instability or an unknown atmospheric cycle. This mutable behavior challenges current models of gas giant atmospheric dynamics. The spot appears as a dark region within a brighter upper layer, visible in both visible and infrared images. It is associated with wind systems that rotate counterclockwise and move quickly through Neptune's atmosphere. The structure spans thousands of kilometers in diameter and has defined edges, though its morphology varies. Its dark color is likely due to the presence of gases or aerosols that absorb sunlight. Despite regular observations from Hubble, its formation remains poorly understood. Neptune's atmosphere is composed mainly of hydrogen, helium and methane, with methane responsible for the planet's blue color. The Great Dark Spot appears within a region of extremely fast winds, which can exceed 2,000 km/h. It is believed that these storms form due to deep thermal instabilities, although this is still debated. Some spots disappear entirely within a few years, while others persist longer, suggesting different formation mechanisms. It is still unknown whether these structures have significant depth or are shallow. A curious aspect is that before disappearing, the spot often migrates in latitude and changes shape. At times, bright clouds form near its edge, suggesting local turbulence and upward movement of material. These clouds, made of condensed methane, serve as indicators of the dynamics beneath the visible surface. They form and vanish alongside the main storm, showing a correlation between atmospheric layers. This complex interaction between dark and light structures is typical of Neptune's weather patterns. The absence of a solid surface on Neptune allows storms to reorganize freely. This favors the formation of vortices, which dissipate as they interact with other jet streams. Unlike Earth's cyclones, which weaken when encountering physical obstacles, Neptune's storms can maintain or alter their shape for weeks or months. This structural freedom adds to the complexity of these phenomena. However, the full cycle of the spot's birth, life, and disappearance is still not well understood. The spot's frequent variation also raises questions about the planet's internal energy. Neptune radiates more heat than it receives from the Sun, indicating an active internal energy source. This energy may fuel deep convection, which, upon reaching the upper layers, generates visible instabilities like the spots. The sudden disappearance of such structures could represent a temporary shift in thermal balance, reflecting how variations in the planet's interior manifest in its outer atmosphere. Observations made by the Hubble Space Telescope since the 90s have been critical for tracking these transformations. Because Neptune is so far from Earth, its visual resolution is limited even with advanced telescopes. However, brightness patterns and spectroscopy allow scientists to infer physical and chemical properties. With the launch of the James Webb Space Telescope, new opportunities have arisen to observe the spot's behavior in infrared. These observations provide more accurate data on temperature, altitude, and composition. The mutable nature of Neptune's dark spots contrasts with the stability of structures on Jupiter and Saturn. This may be related to differences in internal composition and Neptune's weaker magnetic field. It's also possible that supersonic winds create instabilities that prevent fixed structures from persisting. Comparing atmospheric behavior across gas giants helps refine planetary dynamics models. Each planet offers a distinct scenario for energy balance and mass movement. Saturn emits sounds in space. The interactions between Saturn's magnetic field and the charged particles around it produce radio waves that can be converted into sound. These waves, captured by instruments aboard the Cassini and Voyager spacecraft, were transformed into audible tracks for scientific study and public outreach. The resulting sounds are reminiscent of whistles, pulses, and high-pitched tones, with fluctuations in rhythm and frequency. While sound cannot travel through the vacuum of space, radio waves carry data that can be converted into audio. This conversion reveals intricate patterns of electromagnetic activity. The primary source of these waves is Saturn's magnetosphere, an immense magnetic field that captures charged particles. As these particles interact with the field, they produce radio emissions known as Saturn kilometric radiation, SKR. These emissions fluctuate based on the planet's rotation, atmospheric storms, and the positions of its moons. The dynamic nature of the magnetosphere turns Saturn into a natural radio station. Each signal mirrors the changing conditions of space surrounding the planet. The Cassini probe recorded these signals during its decade-long mission. During flybys over the polar and equatorial regions, its instruments detected variations in the intensity and frequency of the radio signals. These fluctuations are linked to events such as plasma ejections, magnetic reconnections, and interactions with moons. Saturn's radio spectrum is so diverse that it can be analysed to study unseen phenomena. Even without direct imagery, the sounds provide insights into both internal and external planetary activities. One of the most fascinating aspects is that the frequency of emissions changes over time. Initially used as a marker for the planet's rotation, the SKR emissions showed variations that contradicted that purpose. The rotation measured through radio waves differed between hemispheres and over time, suggesting the magnetosphere operates independently of Saturn's core. This discovery prompted scientists to rethink how they measure the rotational periods of gas giants. Saturn's emissions are also influenced by its moons, especially Enceladus. The moon releases jets of water and particles into the magnetosphere, altering the electromagnetic environment. This interaction causes changes in the radio signals detected by the spacecraft. It's direct evidence of the interconnected relationship between moons, magnetism, and space dynamics. Saturn's system functions like an intricate circuit of invisible forces. By converting data into audio, researchers can detect patterns that might otherwise be unseen in graphs. The human ear, being sensitive to subtle changes in rhythm and tone, can identify rhythmic pulses, discharges, and oscillations that indicate specific events. Deisonification enhances visual and spectral analysis and bring space science closer to the public. Beyond its educational value, Saturn's sounds hold significant scientific importance. They help study the topology of the magnetic field, the density of particles, and how the space environment responds to solar events. Comparing these radio emissions with other magnetic sources, like Earth's or Jupiter's fields, uncovers both similarities and differences. Acoustic analysis is now a key element of plasma astrophysics, serving as a tool that converts invisible data into sensory experience. Saturn's ability to emit sound reflects its intricate internal and external dynamics. Though not sound in the traditional sense, the converted signals reveal vital aspects of the planet. This proves that even invisible phenomena can be made accessible through scientific translation. The magnetic field becomes a bridge between the planet and human instruments, and sound becomes the universal language of space, and these signals help track changes in the space environment around Saturn. They indicate shifts in radiation, particle flow, and interactions with the solar wind. Ongoing monitoring reveals Saturn's behavior as an energetic system and allows us to predict how the planet reacts to external events. It's a way to listen to the planet's heartbeat from afar. The study of Saturn's sounds shows that even in cold and remote regions, there is intense and measurable activity. The next topic returns to visualizing the bright, icy surface of Enceladus, the moon that reflects nearly all the light it receives. Uranus has rings that are invisible to the naked eye. Uranus has at least 13 known rings, but unlike Saturn's luminous system, they are dark, narrow, and faint. Composed mainly of small particles of ice mixed with dark organic material, the rings reflect very little sunlight. Their low albedo makes them nearly imperceptible in standard telescopic views. They were first discovered in 1777 during stellar occultation, when a star briefly dimmed before and after passing behind Uranus. This unexpected dip in light revealed the presence of thin, sharp-edged rings. Uranus's rings are extremely narrow, with some only a few kilometers wide. They consist of relatively large particles with few micron-sized dust grains, distinguishing them from the diffuse rings of Jupiter or Neptune. The inner rings orbit close to the planet, while outer rings, such as the Epsilon ring, form sharper, more prominent structures. Their composition suggests they are made of ancient debris generated by collisions, indicating a different origin than Saturn's ice-rich rings. Infrared and ultraviolet imaging from spacecraft and Earth-based telescopes have provided a more detailed map of these rings. Observations from Voyager 2's flyby in 1986 confirmed their composition and distribution. Later, Hubble and ground-based observatories track changes in brightness and shape. These studies showed that some rings are tilted or slightly warped. Their evolution appears to be influenced by gravitational interactions with Uranus's many moons. Some rings are maintained by shepherd moons, small satellites, whose gravity confines the ring particles. These moons prevent material from drifting outward or collapsing inward. The gravitational influence creates narrow, stable bands. In the case of Uranus, moons like Cordelia and Ophelia perform this role. Their presence helps explain why the rings have remained sharply defined over time. The system is more organized than it first appears. Despite their faint appearance, Uranus's rings are dynamic and active. They may be shaped by collisions, dust migration, and electrostatic forces. Some particles may originate from eroded moon surfaces or past impacts. Unlike Saturn's young rings, Uranus's ring system appears older and darker. It has likely undergone significant evolution since its formation. The lack of fine dust suggests efficient clearing mechanisms. Due to the ring's dark nature, they are difficult to detect without specialized instruments. Their visibility improves when viewed in backlit conditions, where sunlight scatters off the particles in the rings. During Uranus's equinoxes, ring shadows cross the planet's surface, enhancing their detectability. These rare alignments offer valuable opportunities for detailed imaging. Even then, advanced filters and processing are required. The origin of the rings remains uncertain. They may have formed from a shattered moon or the remnants of captured debris. The irregular structure and composition of the rings support this idea. Over time, collisions and tidal forces could have broken the debris into ring particles. Their current state reflects a long and complex history. Future missions could help clarify their formation and age. Uranus's axial tilt, nearly 98 degrees, adds to the complexity of the ring system. The rings orbit along the planet's equator, which lies nearly perpendicular to its path around the Sun. As a result, their orientation changes dramatically over Uranus's 84-year orbit. Sometimes we view them edge-on, making them nearly invisible. At other times, we see their full tilted profiles. The rings also play a role in Uranus's overall dynamics. They interact with the planet's magnetosphere and influence the motion of nearby moons. Their structure also provides insight into planetary ring formation in general. By comparing Uranus's rings with those of Saturn, Jupiter, and Neptune, scientists refine models of ring stability and evolution. Uranus offers a darker, subtler version of this phenomenon. Despite their lack of brightness, Uranus's ring system is rich in complexity and scientific value. It reveals a hidden side of the planet, one shaped by gravity, collisions, and time. As technology advances, these faint structures become more accessible for study. The next topic will explore Jupiter's vast satellite system, where irregular orbits tell a story of cosmic capture and history. Each fragment continued to orbit Jupiter in a shared path. Over time, gravitational influences and further collisions altered their orbits. These groups include the Ananke, Kame, and Pacific clusters. They orbit far from the planet beyond the major moons. Many of these small moons are only a few kilometers wide. Their faintness and distance make them difficult to detect. Modern surveys using large telescopes have recently expanded the known population. Enhanced tracking has confirmed their orbits and grouped them into families. The increasing moon count reflects advances in detection rather than recent capture. Jupiter likely captured many of these bodies early in its history. The planet's powerful gravity acts like a cosmic net, capable of capturing passing objects. This process likely occurred during the chaotic early phases of the solar system. As Jupiter moved, it may have swept up asteroids and comets. Some of these were slowed by gas drag or collisions and became bound to the planet. The result is a population of satellites with diverse origins. Retrograde orbits are stable under certain conditions, especially at great distances. These orbits help prevent close encounters with other moons. However, they also suggest that the moons were not formed near Jupiter, but were likely members of the asteroid or Kuiper belts. The capture scenarios remain complex and are not fully understood. Simulations continue to explore how Jupiter built its moon system. The irregular moons don't just orbit, they evolve. Their paths are shaped by interactions with the Sun and Jupiter's gravity and each other. Some moons may collide, break apart, or be ejected over long time scales. This evolution reflects the dynamism of planetary satellite systems. The variety of orbital paths illustrates the complexity of gravitational capture. Despite their small size, these moons offer insights into the early solar system. Their composition, surface features, and motion tell stories of migration, collision, and gravitational dynamics. They preserve materials from distant regions of space. Studying them helps scientists understand how gas giants accumulate and manage their satellite systems. They are relics of a more chaotic era. Jupiter's mini-galaxy of moons contrasts with the regularity of its inner moons. While the Galilean moons display organized resonance and stability, the irregular satellites show randomness and variety. Together, they represent a complete spectrum of satellite behavior. Jupiter serves as a model for large planet-moon systems both in our solar system and beyond. The complexity of its satellite system continues to inspire planetary research. As new moons are discovered and classified, Jupiter's role as the moon-rich planet becomes even more evident. These irregular paths, reversed motions, and orbital clusters reflect a gravitational history written across billions of years. The next section may explore how some of these moons influence Jupiter's magnetic field or contribute material to its rings and auroras. Titan features giant dunes made of organic sand. Titan, Saturn's largest moon, has vast dune fields composed not of silica, like Earth's, but of complex organic particles. These dunes stretch for hundreds of kilometers across the equatorial regions, forming parallel ridges shaped by prevailing winds. The particles originate in Titan's upper atmosphere, where ultraviolet sunlight triggers chemical reactions in methane and nitrogen. These reactions produce hydrocarbons and nitriles, which then settle onto the surface. Winds transport this organic material to form dune landscapes. Unlike terrestrial sand, which is made from weathered rock, Titan's dunes are built from soft, sticky organics. The grains are likely smaller and lighter, but capable of accumulating into massive structures due to Titan's low gravity and atmospheric density. Titan's thick, nitrogen-rich atmosphere helps sustain stable wind patterns near the surface. These winds, though gentle by Earth standards, are strong enough to move the grains. As a result, the dunes continue to evolve over time. Radar data from the Cassini spacecraft mapped these dune fields in great detail. They appear mostly in low-latitude regions, particularly around Titan's equator. The dunes are aligned east-west, in line with Titan's atmospheric circulation. Their presence reveals the interplay between surface processes and weather dynamics. Despite the cold temperatures, Titan's surface is surprisingly active. The dunes reflect long-term aeolian transport and organic deposition. The organics that form these dunes are known as tholins, complex molecules produced through atmospheric chemistry. These compounds give Titan its orange hue and coat the surface with dark material. The dune sands are likely made of tholin aggregates mixed with ice or dust. Their composition provides insight into Titan's prebiotic chemistry. Studying them helps scientists understand how complex molecules behave in exotic environments. Titan's dunes are part of a broader climate system involving methane rain, seasonal winds, and surface erosion. During Titan's 29-year solar orbit, equatorial winds shift direction, influencing dune growth. Seasonal changes may also cause brief moisture cycles, altering the cohesion of the dune particles. These effects contribute to the dynamic landscape. Over geological time, dunes migrate, merge, and reshape entire regions. Despite the abundance of dunes, they avoid polar regions where lakes and seas of liquid methane dominate. The surface conditions in these areas are wetter and more stable, preventing the formation of mobile sands. Equatorial regions remain dry and windy, favouring dune development. This spatial separation highlights how Titan's climate creates distinct surface zones, each supporting different types of geological activity. The size of Titan's dunes is comparable to Earth's largest desert systems. Individual ridges can reach 100 meters in height and span several kilometers in length. The total dune-covered area is roughly the size of the Sahara Desert. These features are among the largest wind-formed structures in the solar system, emphasizing the scale of Titan's surface processes. Understanding Titan's dunes aids the search for chemical precursors to life. The grain-like particles contain organic material that was created without biology. Their formation illustrates how planets or moons can accumulate complex chemistry naturally. By analyzing the dunes, researchers explore pathways toward prebiotic molecular assembly. Titan serves as a testbed for organic surface evolution under alien conditions. Future missions like Dragonfly will land on Titan and study its surface directly. One target will be the dune regions, where organic material can be sampled and analyzed. Instruments will investigate grain composition, mobility, and potential interactions with surface liquids. These findings will refine models of dune formation and atmospheric chemistry. Titan's dunes represent a bridge between geology and astrobiology. In a world where water is rock and methane flows like rain, Titan's organic dunes redefine planetary landscapes. Their existence demonstrates that even under extreme cold, dynamic weather and surface interactions occur. As we continue exploring Titan, these dunes offer clues to how organic matter behaves, not just here, but across the universe. The next topic shifts from sand to storm, focusing on Saturn's month-long lightning events. Saturn experiences massive electrical storms that last for months. Some storms last as long as 7 months. These storms, known as Great White Spots, occur periodically and are fueled by deep atmospheric convection. Unlike Earth's short-lived thunderstorms, Saturn's storms persist throughout entire seasons. They release enormous amounts of lightning and heat, reshaping atmospheric bands. Their scale and duration make them key features of Saturn's meteorology. The storms originate deep within Saturn's atmosphere, where water vapor and ammonia interact under high pressure. Rising warm gases trigger vertical convection, lifting material into the upper atmosphere. This process creates bright cloud systems accompanied by intense lightning activity. The energy involved is massive, with strikes occurring thousands of times per hour. Some storms cover areas larger than Earth itself. The Cassini spacecraft detected these storms using both optical cameras and radio instruments. Saturn's lightning generates powerful radio bursts that were recorded from millions of kilometers away. These signals helped map storm duration, location, and evolution. As the storm matures, it can spread longitudinally across the entire planet. The cloud formations associated with the storms are visible in both infrared and visible light. Saturn's climate is shaped by both internal and external forces. Even after storms subside, they leave persistent traces. Cloud disturbances, color shifts, and chemical changes can endure for months or even years. These remnants provide valuable insights into the storm's intensity and energy distribution. Studying these aftereffects allows scientists to model the life cycles of storms. Every event adds to the expanding archive of planetary weather patterns. Understanding Saturn's lightning storms enhances our comprehension of atmospheric processes and gas giants. It offers comparisons for storms on Jupiter, exoplanets, and even brown dwarfs. The data refine our theories of heat transfer, cloud formation, and convective dynamics. Saturn's prolonged storms serve as natural laboratories for studying extreme weather phenomena. From lightning that can last for months to cloud bands stretching across hemispheres, Saturn's storms illustrate the scale of planetary meteorology. They demonstrate that weather in the outer solar system is anything but static. The next topic might delve deeper into Saturn's atmospheric features or shift focus to the icy behaviors of its enigmatic outer moons. Uranus has a moon with deep icy ravines. Miranda, one of Uranus's smaller moons, features some of the most extreme geological formations in the solar system. Its surface is riddled with vast icy chasms that descend as much as 20 kilometers beneath the surrounding landscape, deeper than Earth's Mariana Trench or Mount Everest's peak. These enormous rifts cut through the moon's frozen shell, creating a fractured patchwork of terrain. The surface is so peculiar that scientists once joked it looked as though it had been shattered and reassembled. However, the origin of these features is still unclear. Miranda's odd surface was first observed by Voyager 2 during its flyby in 1986. The spacecraft captured images of towering cliffs, ridges, and polygonal regions known as corona. These areas seem to have diverse geological histories, suggesting multiple episodes of surface reworking. Some features resemble tectonic faults or cryovolcanic flows, while others hint at crustal movements and resurfacing. The combination of terrain types indicates a complicated internal history. The presence of such profound canyons on a small moon is surprising. Miranda's diameter is only about 470 km, roughly half that of Enceladus. Yet despite its size, it displays massive surface deformation, implying that internal forces were once strong enough to reshape its crust. The moon's low gravity should theoretically limit tectonic activity, but the evidence contradicts this expectation. One theory proposes that Miranda was partially melted in the past due to tidal heating from its orbit around Uranus. Gravitational flexing could have generated internal heat, possibly driving cryovolcanism or causing crustal shifts. Once the orbital resonance ceased, the heating stopped, freezing the surface in place. This might explain why Miranda appears geologically inactive but structurally disturbed. The towering cliffs, including Verona Rupes, the tallest known cliff in the solar system, suggest rapid vertical movement. These escarpments may have formed due to faulting or crustal collapse, with gravity much weaker than Earth's. Objects falling from such extreme heights would still accelerate noticeably. These cliffs emphasize the vertical scale of geological forces at work on icy moons. They serve as visual evidence of dramatic internal processes. Miranda's corona are especially intriguing. These oval-shaped features seem to be raised sections of crust surrounded by deep troughs. Their formation may involve diaporism, where blobs of warm ice rise through colder layers, or they could be remnants of ancient impacts or internal restructuring. The true origin remains a topic of debate. Each corona contributes to the mystery of Miranda's history. The Moon's varied surface also suggests that resurfacing occurred in distinct episodes. Some regions are heavily cratered, while others appear relatively smooth and young. This indicates that geological activity likely happened in bursts. It's possible that internal heat surged periodically, reshaping parts of the surface. This episodic activity distinguishes Miranda from more uniformly shaped moons. Despite its fractured surface, Miranda lacks a global magnetic field, and its interior is likely frozen and inactive today. However, the preserved geological features on its crust provide a record of past activity. These remnants offer clues about the Moon's internal dynamics, heating events, and crustal evolution. They also serve as analogues for similar processes on larger icy bodies. Miranda continues to captivate scientists and is a key target for future missions. A closer look could answer important questions about its geological past. High-resolution imaging and subsurface probes could provide clarity on the origins of its cliffs and corona. Understanding Miranda also offers insights into Uranus's entire moon system. Its extreme terrain is a reminder that even small moons can undergo dramatic transformations. As one of the most geologically complex moons of its size, Miranda illustrates how internal forces can reshape icy bodies. Its cliffs and canyons rival those found on much larger worlds. The next topic may shift to magnetic phenomena as we explore Jupiter's intense magnetic field and its far-reaching effects across space. Saturn's rings might be surprisingly young. Saturn's magnificent rings may have formed much more recently than previously believed. Recent research suggests that they are no older than 100 million years, which places their creation during Earth's late Cretaceous period, when dinosaurs still roamed. This challenges the long-standing view that Saturn's rings are as ancient as the solar system itself. Their relative brightness and composition suggest a younger origin. If these findings hold true, the rings would be a fleeting and dynamic feature in Saturn's evolution. The evidence comes from observations by the Cassini spacecraft, which orbited Saturn from 2004 to 2010. Cassini measured the mass, composition, and contamination rates of the ring particles. It discovered that the rings are composed mostly of pure water ice with minimal dust, indicating they haven't been exposed to the harsh environment of space for billions of years. Older rings would be darker and more polluted with micrometeorites. The pristine condition of Saturn's rings points to a recent formation. One possible explanation is that a large icy moon was shattered by a collision or torn apart by Saturn's gravity. The resulting debris could have spread into orbit and formed the rings. Computer models support this idea, illustrating how a moon-sized body could disintegrate into countless icy fragments. These particles would then flatten into the rings we see today. The process may have unfolded in just a few thousand years. The timing of this event coincides with a relatively quiet period in the solar system's dynamic history, where fewer giant collisions took place. This would have increased the chances of ring particles surviving. The ring's temporary nature raises questions about the stability of ring systems. If Saturn's rings are short-lived, other planetary rings might come and go over the course of planetary lifetimes. Cassini also observed the rate at which Saturn's rings are falling into the planet, a process known as ring rain. The particles spiral inward due to Saturn's gravity and magnetic field. As they descend, they vaporize, altering the planet's upper atmosphere. This loss of rings is occurring more rapidly than expected. If this trend continues, the rings could disappear in less than 100 million years. The relative youth of Saturn's rings contrasts with the planet's age of over 4.5 billion years, suggesting that the rings are a temporary feature in Saturn's long history. Their brief existence makes them particularly valuable for study. Despite their impermanence, Saturn's rings provide crucial insights into disk dynamics. They act as natural laboratories for studying collisions, accretion, and gravitational sculpting. The embedded moonlets and gaps illustrate how material behaves under Saturn's influence. These features mimic processes found in protoplanetary disks around young stars. Saturn's rings, therefore, offer a bridge between planetary and stellar formation theories. The composition of the rings is not uniform. Inner regions are denser and brighter, while the outer rings are more diffuse. This structure may reflect the distribution of original debris or the evolution of the material over time. Variations in the density, thickness, and particle size help reconstruct the history of the ring system. Some scientists still advocate for an older ring system that has been periodically renewed, with collisions constantly replenishing the material and keeping the rings young. However, the measurements of mass and purity made by Cassini challenge this theory. The debate continues, and future missions may provide a clearer answer. For now, the prevailing view is that Saturn's rings are relatively young. The realization that Saturn's rings are both recent and temporary adds a dynamic chapter to planetary science. No longer seen as ancient remnants, the rings are now understood as evolving features within an active system. The next topic may examine internal planetary processes such as diamond rain or helium separation deep within the gas giants. Uranus glows in infrared light but is barely noticeable in visible light. In visible light, Uranus appears faint and lackluster, with a pale bluish-green tint that reveals few details of its atmosphere. However, when examined in the infrared spectrum, the planet unveils intricate bands and dynamic weather systems. Infrared imaging uncovers temperature differences and cloud structures concealed beneath the visible haze. These bands indicate regions of varying thermal emission and atmospheric depth. Observations from Earth, along with the Hubble and James Webb telescopes, reveal a surprisingly lively atmosphere beneath its surface appearance. Infrared wavelengths emphasize subtle contrasts not visible in regular light, such as warm and cool areas tracking weather systems. At certain latitudes, transient bright spots and darker zones appear, suggesting vertically structured clouds and thermal anomalies. These differences indicate atmospheric turbulence and upward motion, providing insight into how energy is transferred from the interior to the outer atmosphere. Uranus completes a rapid rotation every 17.2 hours. However, its visible atmosphere remains subdued. Infrared observations, on the other hand, reveal underlying jets and circulation zones. These bands reflect variations in emission intensity, with their visibility depending on the viewing angle and seasonal tilt. During specific seasons, deeper thermal bands become more pronounced, demonstrating that Uranus's internal dynamics are hidden in visible light but are revealed by thermal radiation. Seasonal changes on Uranus also affect infrared patterns. As the planet orbits the Sun over 84 years, the tilt exposes each hemisphere to extended periods of sunlight or darkness. Infrared maps capture the resulting temperature shifts at mid-latitudes. These changes reshape atmospheric zones and cloud thickness, clarifying the relationship between sunlight, internal heat, and thermal emissions. Ground-based telescopes with adaptive optics have played a vital role in advancing this understanding. They regularly observe Uranus in near-infrared wavelengths, revealing its structure and evolution. These observations track seasonal changes and unexpected events, such as storms and bright spots, offering essential context alongside space missions. The combined observations create a continuous record of atmospheric transformations. The contrast between the visible plainness and the infrared activity highlights Uranus's unique character. It demonstrates that visible appearance does not always reflect internal processes. The planet conceals its dynamism beneath a uniform outer layer, while infrared observations provide a window into deeper atmospheric behavior. This insight allows scientists to study meteorology that would otherwise remain hidden. Understanding Uranus's atmosphere through infrared observations enhances planetary climate models. It offers useful comparisons with other ice giants and aids in exoplanet research. Temperature gradients, cloud patterns, and emission behaviors feed into simulations, helping predict weather on cold, distant worlds. Uranus serves as a reference for interpreting exoplanetary atmospheres with similar conditions. Future missions to Uranus may deploy infrared spectrometers to map its atmospheric composition and thermal structure. Instruments in orbit or via flybys could reveal how hydrogen, helium, and methane influence emissions and help determine vertical mixing rates and cloud altitudes. Such missions would deepen our understanding of the hidden dynamics of ice giants. By correlating infrared features with atmospheric models, researchers can estimate wind speeds, cloud chemistry, and circulation. Even without dramatic visible changes, Uranus reveals its secrets through thermal imaging. Its clouds, although subtle, are active, shaped by processes beneath the upper layer. The planet exemplifies how appearances can be deceiving. Uranus's infrared glow emphasizes the significance of multi-wavelength observation, reminding us that scientific investigation must go beyond what is visible to the eye. Beneath its calm surface lies an active world of weather and motion. The next topic will explore Jupiter's interior, uncovering hidden metallic layers under extreme pressure. Jupiter has a liquid metallic interior. Deep within the planet, hydrogen faces such extreme pressures that it transforms into a liquid metallic state. Under pressures more than 3 billion times that of Earth's atmosphere, hydrogen's electrons become detached, allowing them to flow freely, much like metals. This layer of metallic hydrogen acts as a conductor of electricity and is vital for generating Jupiter's strong magnetic field. This process begins hundreds to thousands of kilometers below the cloud tops within the planet's mantle. Though invisible from the outside, this layer defines Jupiter's internal behavior. The metallic hydrogen shell is encased by molecular hydrogen and helium above it, forming distinct layers. As one descends into the planet, pressure and temperature rise sharply. Temperatures soar to tens of thousands of degrees Kelvin, and in this violent environment, hydrogen behaves as a fluid metal. Convection within this layer mixes heat outward, generating currents that create a powerful magnetic dynamo effect. Jupiter rotates swiftly, completing a full spin in just under 10 hours, which enhances the dynamo effect. The combination of rotation, metallic flow, and convection results in the largest and most intense magnetic field in the solar system. This field extends millions of kilometers outward, shaping radiation belts and shielding the inner planets. The dynamo is self-sustaining, powered by internal heat and rotational momentum. Gravitational and magnetic data from NASA's Juno mission have confirmed the depth and behavior of Jupiter's metallic hydrogen layer. Variations in the magnetic field and gravity suggest complex flows and possibly layered convection. This information helps us model the internal structure of Jupiter with unprecedented precision, validating predictions made decades ago based on planetary physics and high-pressure experiments. Laboratory studies, such as diamond anvil and shock compression tests, replicate the conditions found in Jupiter's interior, confirming that hydrogen transitions into a metallic form under extreme pressure and temperature. The resulting conductivity and opacity properties match the models used to describe Jupiter. The behavior of metallic hydrogen influences Jupiter's thermal evolution. Its conductivity allows heat generated at the core to rise efficiently, sustaining the planet's long-term luminosity and supporting atmospheric phenomena. It may also affect seismic waves impacting planetary modes. Understanding metallic hydrogen's properties is crucial for interpreting future measurements of internal planet dynamics. As metallic hydrogen mixes with helium, phase separation could occur. Helium might form droplets that fall toward the core, releasing gravitational energy. This process adds internal heat and affects the stability of the magnetic field. It also contributes to compositional stratification within the planet. This phenomenon of helium rain is another ongoing scientific question tied to metallic hydrogen dynamics. Jupiter's liquid metallic hydrogen layer serves as an analogue for exotic states of matter, resembling conditions found in stellar cores and giant exoplanets. Studying it provides valuable insights for theories across astrophysics and condensed matter physics. Jupiter functions as a laboratory for studying extreme pressure-induced states of matter. These observations and models help us better understand planets beyond our solar system. Despite its position deep beneath the surface, metallic hydrogen impacts the planet's surface. It sustains magnetic shielding, auroras, radiation belts, and plasma environments. Its dynamics affect layers of molecular hydrogen, clouds, and extend outward into space. Jupiter's visible storms and magnetic shield owe their existence to this hidden metallic fluid. Exploring Jupiter's interior, especially its metallic hydrogen layer, is a major focus for planetary science. Future missions may involve probes or remote sensing to detect seismic waves or trace elemental distributions. Enhanced models and observational techniques may reveal the true nature of Jupiter's core, mixing layers, and dynamo processes. Beneath the clouds lies a world governed by extreme physics. Saturn's winds reach nearly the speed of sound, At Saturn's equator, winds can reach impressive speeds of about 1 to 800 km, almost matching the speed of sound on Earth. These winds form part of a global pattern of zonal jets, with alternating east-west bands encircling the planet. Saturn's rapid rotation, with a day lasting only about 10.7 hours, generates strong Coriolis forces that organise these jet streams. Although Saturn is cooler and less dense than Earth, its swift rotation amplifies atmospheric dynamics. This results in wind speeds that rival supersonic conditions on Earth. Ground-based observatories, along with data from the Cassini mission, have measured these winds by tracking cloud movements. Bright clouds and storm systems act as markers for wind flow at different latitudes. Equatorial jets are particularly persistent and stable, showing minimal variation over decades. Their consistency provides valuable insights into atmospheric circulation under extreme rotational influence. These jet streams shape atmospheric bands and cloud structures visible from space. Saturn's equatorial winds are powered by both internal heat and solar energy. Heat rising from the planet's interior drives convection, lifting parcels of gas into the atmosphere. Once in motion, Saturn's rapid rotation twists these gas parcels into longitudinal jets. The interplay between vertical convection and lateral stretching generates high-speed wind zones. These jets focus energy into narrow bands that persist for extended periods. Unlike Earth, Saturn lacks a solid surface to slow or disrupt the jets. This lack of friction allows zonal flows to build and sustain unusually high speeds. Wind speeds peak at specific latitudes where jet interactions strengthen the flow. Atmospheric shear at the edges of the jets may also produce turbulence and cloud formation, though the overall band structure remains stable across seasons. Seasonal changes on Saturn have minimal effect on the winds. Despite variations in sunlight distribution over its 29-year orbit, the equatorial jets remain steady. This suggests that internal energy sources play a more significant role than solar influences. Long-term observations confirm that the speed and structure of these winds are remarkably resistant to external disruptions. Storms like the Great White Spot can temporarily disturb the wind bands, injecting energy into the surrounding regions and altering local wind patterns. After such events, the equatorial jets can absorb the disturbance energy and restore their original strength. This resilience highlights the adaptable nature of Saturn's atmospheric circulation. The depth of these jets remains under investigation. Some models suggest they may extend hundreds or even thousands of kilometers deep. Gravity field measurements taken by Cassini support the presence of deep-reaching atmospheric flows. If true, this would imply that Saturn's winds are not just surface-level phenomena, but are integrated into the planet's structure. Modelling these deep jets helps refine our understanding of Saturn's internal composition. Saturn's wind speeds approach Mach 0.9 in terrestrial terms. Such extreme conditions create shock-like shear zones at the jet boundaries. These zones may generate small-scale turbulence and influence energy distribution. Despite this, the planet remains strikingly calm in appearance unless disturbed by storms. This paradox of high-speed yet serene-looking conditions is unique to gas giants. Studying Saturn's winds provides scientists with insights into similar phenomena on Jupiter, Neptune, and exoplanets. Rapid planetary rotators can develop jet structures that shape weather and climate systems, and Saturn serves as a prime example for studying these dynamics. By analysing wind patterns, researchers enhance their models of atmospheric physics in rotating gaseous bodies. Saturn's supersonic winds show how rotation and internal heat intertwine to produce intense atmospheric flows, challenging assumptions based on terrestrial dynamics. The next topic will delve into Uranus's unusual axial behaviour and atmospheric irregularities under its lateral rotation. Uranus experiences orbital irregularities. Due to its extreme axial tilt of about 98 degrees, Uranus experiences a form of orbital stalling during solstices. As the planet rolls through space, its poles point almost directly at the Sun twice each Uranian year. This results in one pole receiving continuous sunlight for over 42 Earth years, while the opposite pole remains in darkness. This positioning disrupts the normal circulation of sunlight, creating prolonged periods of thermal imbalance between hemispheres. During the solstice alignment, one hemisphere warms steadily, while the other cools slowly. This results in persistent temperature gradients across latitudes. However, Uranus shows surprisingly little atmospheric response in visible light, suggesting that internal dynamics redistribute heat efficiently. Infrared observations, on the other hand, confirm seasonal temperature contrasts. The energy imbalance builds slowly over the years before dissipating after the solstice. The unusual tilt also affects the planet's rotational dynamics. Its spin axis lies nearly perpendicular to the solar system's plane, making Uranus behave like a rolling ball as it orbits the Sun over 84 Earth years. This introduces orbital phenomena not seen on other planets. The equatorial regions of Uranus receive alternating extreme solar exposure, leading to temporary stalled zones of illumination. These stalled conditions halt the progression of solar seasons near the poles. The midnight sun effect on Uranus persists for over 4 decades, much longer than Earth's polar regions. During the solstice, atmospheric circulation near the poles may even reverse. However, since Uranus's atmospheric response is muted, scientists conclude that heat is redistributed more uniformly. Infrared data obtained during Uranus's 2007 equinox revealed shifts in thermal emissions, indicating that as the sun crossed the equator, mid-latitude warming occurred while cooling was observed over the poles, signifying heat migration. These findings support the idea that stalled regions flip after the equinox. Predictions suggest a similar cycle will take place again, maintaining overall thermal balance. These unusual solar configurations also influence Uranus's magnetosphere and plasma environment. The planet's tilted magnetic field interacts differently with the solar wind during pole-on orientations, altering the shape of the magnetosphere and affecting auroral activity. Cassini-like studies at Uranus have observed seasonal shifts in magnetosphere geometry, driven by solar exposure rather than internal dynamics. Despite the extreme axial tilt, Uranus lacks extreme seasonal weather, likely due to its low internal heat. Its internal energy output is minimal compared to Neptune's, resulting in less dramatic solar-induced seasons. The planet's dull appearance in visible light supports this theory. Still, settled seasonal shifts in cloud composition and strength have been observed in infrared and methane bands. The stalling of sunlight near solstices also affects the illumination of Uranus's moons and rings. These bodies alternately receive and lose solar exposure over long periods. During solstices, the rings appear edge-on or highly illuminated, affecting their thermal behavior and visibility from Earth. Monitoring these changes offers insight into seasonal dynamics across the entire system. Studying Uranus's stalled seasonal cycles enhances our understanding of planetary atmospheres under extreme axial conditions. It shows how tilt and orbital motion can override typical energy distribution. Uranus serves as a natural laboratory for studying physics under unusual orientations, and its irregular behavior challenges generic climate models. By exploring Uranus's axis-driven seasons and stalled states, we gain a better understanding of the role axial tilt plays in planetary dynamics. The planet serves as a reminder that orientation is as important as composition. The next topic might explore how this tilt influences magnetism, rings, or internal heat transport. Jupiter redistributes asteroids across the solar system. Jupiter's immense gravitational field plays a crucial role in shaping the structure of the asteroid belt. As asteroids orbit the Sun, those near Jupiter's path are perturbed by its gravity, altering their orbits. Some are trapped in stable regions called Lagrange points, located 60 degrees ahead and behind Jupiter in its orbit, where solar and planetary gravity balance. These regions host the Trojan asteroids, which are divided into 2 main groups, the Greek camp leading Jupiter and the Trojan camp trailing it. These groups follow the planet's orbit in a stable configuration that has remained intact for billions of years. Unlike the scattered asteroid belt, Trojans remain in tightly packed swarms, offering a glimpse into early solar system material, possibly predating the planets. Their preservation owes much to Jupiter's stabilizing influence. Jupiter's gravitational effect extends far beyond the Trojans. It also shapes the boundaries of the main asteroid belt, clearing specific regions known as Kirkwood gaps. These gaps represent orbital resonances, where asteroids experience repeated gravitational tugs from Jupiter. Over time, these forces destabilize their orbits, leading to their ejection from the belt or displacement into new paths. Some become near-Earth objects or long-term Trojans. The movement of asteroids under Jupiter's influence is governed by orbital mechanics and resonance dynamics. Some objects shift gradually through the Yarkovsky effect, where sunlight subtly alters their spin and drift. Once near a resonance, Jupiter's gravity takes over. This process explains why certain asteroids appear in locations different from their likely origin. Jupiter serves as an asteroid gatekeeper, protecting the inner planets by diverting objects but also sending some toward Earth-crossing orbits. The combination of gravitational steering and resonance effects allows Jupiter to shape the risk landscape for impacts over geological time, influencing planetary cratering rates. Jupiter is both a barrier and a bridge in solar dynamics. The Trojan swarms themselves vary in size, shape, and composition. Some are several hundred kilometers wide, while others are merely boulders. Spectral analysis reveals that many are dark, carbon-rich bodies similar to those found in the outer asteroid belt. Their composition suggests a possible origin in the early, colder solar system. Studying them helps trace material exchange between planetary zones. NASA's Lucy mission is on its way to study multiple Trojan asteroids. It will investigate their surface chemistry, structure, and collisional history. By sampling both the leading and trailing groups, scientists aim to reconstruct how Jupiter's gravity captured these bodies. Lucy will provide the first close-up view of this ancient population. Trojan asteroids serve as a natural laboratory for studying orbital stability. Their long-term presence in Lagrange points illustrates how gravitational balances preserve structures over eons. These principles also guide satellite positioning and planetary formation models. By studying Trojans, we can learn how planets shape their orbital environments. Jupiter's influence extends to other planets as well, with Neptune and Mars possessing smaller, less stable Trojan-like populations. Jupiter remains the quintessential gravitational redistributor. Its role in asteroid relocation is one of the most enduring aspects of its cosmic influence. The redistribution of asteroids by Jupiter reflects the intricate balance of motion and mass within our solar system. Through gravity alone, it organizes chaos into structured patterns, Trojan swarms, resonant gaps, and asteroid families. The next topic will examine Saturn, where ice behaves with surprising clarity. Saturn holds some of the purest ice found anywhere in the solar system. Its rings and the small moon Enceladus boast icy surfaces that reflect nearly all incoming sunlight, with albedo values approaching 9%. This high reflectivity indicates the absence of dust, organic compounds, or weathering. Unlike ice on Earth, which is often contaminated by air, minerals, or biological materials, Saturn's ice is exceptionally clean. This purity makes it scientifically significant and visually brilliant. Cassini spectrometers confirmed the remarkable cleanliness of Saturn's ring particles. The ice primarily consists of water with only trace amounts of impurities detected. The rings gleam brightly in both sunlight and infrared, showing minimal absorption from darker materials. This suggests the ice is continually refreshed or shielded from contamination. Its unblemished state allows scientists to examine nearly pristine water ice in space. Enceladus, one of Saturn's inner moons, shares similar characteristics. Its surface is coated in fine-grained ice ejected from the South Pole geysers. These geysers release water vapor and ice particles from a subsurface ocean. As the material falls back to the surface, it blankets the terrain in clean, radiant snow. This cycle continuously renews the moon's reflectivity, keeping it one of the brightest objects in the solar system. Enceladus's plumes not only refresh its surface but also contribute to Saturn's E-ring. The particles expelled escape the moon's gravity and populate the larger ring system, making Enceladus both a source and a mirror for icy material. The shared properties between the moon and ring help explain their purity, suggesting a continuous feedback loop of fresh ice deposition. Unlike other moons, Enceladus lacks a thick regolith layer that traps impurities. Its active surface is constantly resurfaced by cryovolcanic spray, preventing the buildup of darker material over time. As a result, Enceladus avoids the usual darkening seen on other icy bodies. Its reflectivity serves as a marker for ongoing geological processes below the surface. The purity of Saturn's ice offers valuable insights into the system's history. If the rings are indeed young, as some studies suggest, their freshness is easier to explain. However, if they are ancient, there must be a continuous mechanism for cleaning or replenishing the ice. This ongoing debate is directly tied to the composition and brightness of the ring particles. Their reflective power is more than just aesthetic, it tells a deeper story. The small particles within Saturn's rings vary from centimeters to meters in size. They constantly collide, fracture, and recoalesce, maintaining a dynamic system. These interactions wear away contaminants and expose fresh ice. The thin vertical thickness of the rings helps prevent the accumulation of external dust, aiding in the preservation of their signature shine. Measuring albedo across different ring sections reveals variations in purity. The inner B ring is the brightest, while outer regions darken slightly. This gradient may reflect differences in exposure to solar radiation, micrometeorite bombardment, or aging processes. These changes are key to modelling the physical evolution of the rings over time. The clean ice also plays a crucial role in regulating temperature. The highly reflective surfaces absorb very little sunlight, keeping the ring temperatures lower than expected. This thermal behaviour affects the stability of the rings, particle movement, and the ability to host embedded moonlets. Enceladus benefits from surface cooling due to its icy covering, and these thermal dynamics shape the structure of the entire system. Saturn's pure ice is more than just a visual phenomenon. It acts as a window into geological activity and cosmic recycling. Through geysers, collisions, and orbital resonance, the icy material remains pure and bright. Neptune spins faster than Earth. Despite being nearly 4 times Earth's diameter, Neptune completes a full rotation in just about 16 hours, making it one of the fastest spinning planets in the solar system. Its rapid rotation generates strong Coriolis forces, contributing to dynamic atmospheric motion. These effects are visible in banding storms and long-lasting vortex systems. The planet's swift spin challenges the assumption that rotation scales with planetary size. Neptune's internal structure supports its fast rotation. Made up mainly of hydrogen, helium, water, and other ices, its interior allows for efficient angular momentum distribution. The fluid layers within the planet can shift and rotate independently, especially in the atmosphere. These layers interact with deeper interior processes, helping Neptune maintain a steady yet rapid rotation. Observations show minimal variation in the planet's rotational speed over decades, and cloud tracking studies have confirmed the rotation period using features like storms and bright spots. These structures move across Neptune's visible surface, allowing scientists to estimate internal rotation rates. Unlike Earth, Neptune's lack of a solid surface complicates this measurement, but consistent patterns provide reliable estimates of the planet's spin. Fast rotation directly contributes to Neptune's powerful weather. The planet experiences supersonic wind speeds that exceed 200 km per hour in certain regions. These winds are the result of interactions between solar energy, internal heat, and rotational dynamics. The resulting jet streams form stable belts and vortices. The equatorial and polar regions rotate at different rates, generating turbulence. The rapid spin also affects Neptune's shape, making it noticeably oblate, wider at the equator than at the poles. The centrifugal force created by rotation flattens the poles and bulges the equator, which in turn influences atmospheric behavior and gravitational field strength. This must be accounted for in internal structure models. Neptune's fast day has implications for its magnetosphere. The rapid rotation twists magnetic field lines, creating dynamic interactions with solar wind. These interactions shape the planet's bow shock and radiation belts and generate auroras at the poles, though they are much fainter than Jupiter's. The rotational period influences how Neptune's magnetic field evolves, and the dynamo driving the field may exist in a shell of conductive water-ammonia fluid. This layer, compressed by high pressure, rotates with the planet's deep interior. As it moves, it sustains the magnetic field and impacts charged particle behavior. This results in an off-center, tilted magnetic field, which is different from the Earth's. Fast planetary rotation also limits the time for solar heating at any one location. Combined with the low solar flux due to Neptune's distance, this results in remarkably uniform atmospheric heating. The planet's rapid rotation mixes heat quickly between day and night sides, maintaining even temperature distribution and enhancing convective processes. This supports active, deep-seated weather systems. The 1989 Voyager 2 flyby provided much of the current understanding of Neptune's rotational dynamics, with its instruments tracking radio emissions and observing visible features. These findings are the foundation for current models of Neptune's interior and rotation. Future missions may refine our understanding of Neptune's dynamics, but the fundamental conclusion remains: Neptune spins very fast. Neptune's 16-hour day defies expectations for a planet of its size and distance. Its rapid rotation powers winds, shapes its magnetic field, and contributes to its oblate form. This dynamic behavior illustrates how internal composition and angular momentum define planetary characteristics. Uranus may have supercritical salt water deep inside. Beneath the cold, thick atmosphere of Uranus lies a region where water could exist in a supercritical state. Under extreme pressures and temperatures, water transitions into a phase that is neither liquid nor gas. Instead, it behaves as a dense fluid, with gas-like diffusion and liquid-like density. This supercritical water might mix with ammonia, forming conductive layers in the planet's interior. These layers influence heat transport, magnetism, and the planet's structural stratification. The presence of supercritical water is inferred from planetary models and laboratory simulations. Pressures inside Uranus exceed 100,000 atmospheres, and temperatures surpass thousands of Kelvin. Under these conditions, water and ammonia can no longer exist as distinct phases. Instead, they blend into a fluid that lacks a clear boiling point. This unique state alters how energy and particles move through the planet's interior. This supercritical layer likely exists in a shell surrounding a rocky core, with a molecular envelope composed of hydrogen, helium, and methane above it. As heat from the core rises, it encounters the supercritical layer, which could conduct electricity and transport heat via convection. The presence of ammonia increases conductivity, which is essential for generating the planet's magnetic field. It's a vital component of Uranus's internal dynamics. Uranus's magnetic field is highly unusual. It is tilted by 59 degrees from the rotational axis and offset from the planet's center. Such geometry suggests a dynamo operating in a thin fluid shell, like supercritical water ammonia, rather than the traditional iron core dynamo seen on Earth. The conductivity and motion in this region sustain Uranus's irregular magnetic field. The structure of this zone directly impacts the magnetic field's behavior, and supercritical fluids help explain the layered structure observed in density models. Unlike solids or conventional liquids, supercritical fluids allow gradual transitions between interior layers. This stratification may reduce mixing and create thermal barriers within the planet, trapping heat and explaining Uranus's low thermal emission. Unlike Neptune, Uranus emits very little excess heat. The supercritical layer could act as an insulator. Salt content from the rocky core's dissolution may increase electrical conductivity, further supporting the magnetic field's development. Understanding supercritical water layers is crucial for exoplanet research. Many exoplanets are Uranus-sized and may possess similar internal structures. Modeling supercritical behavior helps predict magnetic properties, heat loss, and planetary evolution. Laboratory experiments under high pressure validate some of these predictions. Uranus serves as a model for planets rich in water, specifically ice giants. Direct measurements of the supercritical layer are not yet available. All assumptions are based on gravitational, magnetic, and atmospheric data. A future spacecraft equipped with magnetometers and gravity sensors could provide answers to crucial questions. Although deep probes would face extreme pressure and temperatures, even flyby data could help refine existing models. The goal is to determine how accurately we can predict supercritical behavior from a distance. The supercritical state also affects Uranus's seismic and acoustic characteristics. If waves travel through this layer, they could reflect or scatter differently. These interactions might reveal boundaries between distinct zones. Measuring them would require advanced instruments or long-term orbital observations. Each discovery helps map the interior of planets more accurately. Uranus's potential supercritical saltwater layer is a perfect example of the unique physics found in ice giants. It shows how planetary chemistry, pressure, and temperature combine to create conditions unlike anything on Earth. These internal characteristics influence surface magnetism, energy movement, and long-term evolution. Does Jupiter experience diamond rain? Research suggests that Jupiter's extreme internal pressures and temperatures could transform molecules into solid diamond-like structures. Under intense compression, hydrogen and methane break down, allowing carbon atoms to bond and form crystalline patterns. Deeper inside, silicon and carbon may combine to form silicon carbide, a precursor to diamond creation. These dense particles might fall deeper into the planet's interior. Though still a theoretical idea, lab simulations and modelling back up its feasibility. Experiments involving shock waves and diamond anvil cells recreate conditions similar to those in Jupiter's core. Under these pressures, methane decomposes and carbon forms into nano-sized diamond dust. These particles are too dense to remain suspended, so they descend further into the planet. This gradual diamond rain could alter Jupiter's composition over time, potentially impacting its internal structure and energy distribution. A similar process is expected in Jupiter-like exoplanets. Diamond rain might be common in giant planets rich in methane, expanding our understanding of chemistry in exoplanets. The diamond rain theory broadens our comprehension of crystallization processes in planetary interiors. The particles that fall could also influence Jupiter's heat profile, releasing gravitational energy as heat during their descent. While not a primary heat source, it could play a role in the planet's internal thermal balance. Combined with metallic hydrogen convection, diamond rain could help shape Jupiter's deeper dynamics. However, detecting this phenomenon directly is currently impossible. All evidence is based on theoretical models and experimental data. Planetary scientists simulate long-term effects to estimate whether diamond layers could accumulate over time. While surface observations cannot reveal internal precipitation, understanding the process provides insights into Jupiter's internal structure. It remains an intriguing element in the planet's complex puzzle. This hypothesis contrasts with traditional rocky planets. For example, Earth lacks such deep organic carbon layers, while giant planets support exotic crystal formations far beyond Earth's norms. These processes occur under extreme conditions unique to gas giants, illustrating the diversity of planetary chemistry across the universe. Jupiter's potential diamond rain emphasizes its geophysical complexity, adding to processes like metallic hydrogen layers and helium rain. Together, these factors contribute to the planet's magnetic field, thermal emission, and evolution. Each layer in Jupiter's interior forms part of a multi-phase system that is unlike anything on Earth. The concept also shows how public fascination with extraordinary planetary phenomena fuels scientific research. Diamond rain captivates the imagination, adding allure to otherwise invisible deep processes. Its significance, however, lies in its scientific relevance. It serves as an entry point for exploring high-pressure chemistry and planetary physics. Saturn has a moon that creates its own mini-atmosphere. Tethys, one of Saturn's medium-sized moons, emits particles through cold jets, forming a thin exosphere around it. These jets release water vapor and organic molecules into space. Although the exosphere is extremely faint and not breathable, it represents a self-generated gas envelope. The particles originate from surface ices and possibly subsurface reservoirs. As a result, it creates a miniature atmosphere sustained by active surface processes. Cassini's flybys detected both neutral and ionized water molecules around Tethys. Instruments measured vapor concentrations peaking on the day side. The jetting appears intermittent, likely triggered by micrometeorite impacts or temperature fluctuations. Organic trace gases accompany the water, suggesting complex surface chemistry. This exosphere is one of the few known among Saturn's mid-sized moons. Despite its faintness, Tethys's exosphere has important scientific implications. It highlights the active surface-space coupling, where particles can be influenced by Saturn's magnetosphere and contribute to its plasma population. The thin atmosphere is both a local feature and part of the broader planetary system. Surface temperatures on Tethys cause ice sublimation when exposed to sunlight. Small pits or fractures may vent gas when warmed by the sun. These vents act like tiny geysers, though without high pressure or heat. This cold venting mechanism resembles the processes observed on Enceladus, but on a smaller scale. It shows that icy moons can release gas at low energy. The water vapor and organics created affect the moon's immediate surroundings. The vapor molecules can travel, falling back to create local frost, or light on Saturn's ring particles or magnetosphere. Over time, Tethys contributes to the gas and dust environment around Saturn. Though minimal, it demonstrates continuous surface renewal. Comparisons between Tethys, Enceladus, and Mimas show a spectrum of ice-moon activities. While Enceladus features powerful plumes, Tethys shows a gentler release. Each moon's exosphere reflects its unique geological characteristics. Tethys's faint atmosphere offers clues about subsurface reservoirs and thermodynamics. Future missions may refine our understanding by analyzing exospheric composition and changes over time. Instruments could monitor jet activity, temporal shifts, and interactions with magnetospheric particles. This data would help assess subsurface ice pockets and gas pathways, potentially revealing whether organic-rich reservoirs are common. Despite its faintness, Tethys's exosphere marks the presence of local atmospheric processes on a small moon. It demonstrates that even tiny moons can host active surface gas cycles, blurring the line between inert worlds and geologically active bodies. Tethys emerges as a dynamic yet subtle player. Understanding exospheres on moons like Tethys aids studies on habitability and cryovolcanism. It raises questions about chemical transport, freeze-thaw cycles, and ice integrity. Each faint atmosphere expands our understanding of volatile behavior in cold environments. Tethys's miniature atmosphere may be modest but scientifically significant. Together, Tethys and other icy moons illustrate the variety of atmospheric phenomena across the solar system. Even small bodies can exhibit gas release from their surfaces, reminding us that planetary activity is not confined to larger worlds. Neptune has a moon with extreme temperatures. Triton, Neptune's largest moon and its only major retrograde satellite, displays geysers of nitrogen ice that shoot hundreds of meters high, even though its surface temperatures are below 135 degrees. These eruptions happen near the sun-facing poles during seasonal warming, indicating ongoing geological activity. The plumes release material and form dark streaks on the surface. Triton's thin nitrogen atmosphere supports pressure cycles that drive these geysers, making it one of the coldest yet most active worlds in the solar system. The geysers were first observed by Voyager 2 in 1999, with plumes reaching nearly 8 kilometers above the surface. The eruptions follow a process where solar heat penetrates dark ice or surface material, vaporizing nitrogen pockets beneath. This pressurizes the environment and forces nitrogen gas to escape through vents. As the gas escapes, it carries ice grains, forming tall, frost-laden plumes. This seasonal process links solar exposure with eruptive activity. Triton's retrograde orbit, which moves opposite to Neptune's rotation, suggests it was captured, likely from the Kuiper belt. This unusual history likely contributed to internal heating and geological activity. Combined with seasonal solar input, it explains how a frozen moon sustains geysers. The eruptions leave behind dark reddish streaks known as cantaloupe terrain, giving the surface its unique appearance. These features change with the seasons, indicating ongoing surface renewal. Temperatures on Triton are among the lowest in the solar system, hovering near the triple point of nitrogen. Despite this, eruptions continue during Neptune's summer months, with seasonal sunlight providing enough energy to sublimate nitrogen ice through insulated layers. Darker regions absorb heat more efficiently, functioning like solar collectors. This reveals how even slight variations in solar forces can drive activity in extremely cold environments. Triton's atmosphere, though thin, fluctuates with geyser activity. During eruptions, localized pressure increases, causing winds and regional movement. Observations show temporary brightening in regions connected to plume activity. The nitrogen exosphere expands and contracts in a seasonal cycle. Though short-lived, this exospheric activity demonstrates how a frigid moon can sustain atmospheric change. Deep beneath the surface, residual heat from tidal interactions may still influence geological processes. While Triton has a Pluto-like orbit, its interior may remain partially warm. This heat supports subsurface volatiles and possibly a thin ice layer with some mobility. The combined effect of internal heat and solar energy maintained surface dynamics, allowing Triton to remain geologically active despite the extreme cold. Triton's geysers also contribute to a seasonal polar haze and thin clouds. Vapor particles rise and condense, forming hazes visible from space. These hazes alter the moon's albedo and thermal properties by redistributing ice deposits. This cyclical deposition refreshes darker patches on the surface. Observing weather driven by these plumes provides valuable insight into how volatile materials are redistributed on icy bodies. Despite being incredibly cold and distant, over 30 astronomical units from the Sun, Triton challenges our expectations of geological inactivity. It shows that cryovolcanism can function in freezing environments. Triton's unique orbit and composition combine to produce rare geological phenomena, making it one of the most fascinating icy moons in the solar system. Future missions to Triton could reveal subsurface reservoirs, geyser mechanics, and atmospheric cycles. High-resolution imaging and mapping would help clarify surface renewal rates, and sampling the plumes could provide clues about the interior composition. Triton reminds us that even the coldest worlds can reveal dynamic behaviors. Triton exemplifies how extreme temperatures don't preclude geological activity. Its nitrogen geysers and thin atmosphere show that distant icy bodies can be scientifically rich. As exploration continues, Triton could become a prime candidate for studying cryovolcanism and astrobiological potential. Uranus could experience helium precipitation. Models suggest that within Uranus's icy mantle, helium may separate from hydrogen under high pressure and temperature, forming droplets that fall into deeper layers. As the planet cools, helium becomes immiscible and condenses. These droplets then sink, releasing gravitational energy and altering the planet's internal composition. This process impacts heat transport and could influence Uranus's thermal evolution. It mirrors similar behavior proposed for Jupiter and Saturn, although it may differ in scale and effect on Uranus. Helium rain in Uranus could help explain its unusually low heat emission. Uranus radiates almost no excess heat compared to the energy it receives from the Sun, an anomaly among gas giants. If helium separates and sinks, it could trap heat or disrupt convective flow. This layer of helium-rich fluid could slow down internal mixing, preventing much of the internal heat from escaping into space. Studies of giant planets consider helium precipitation to understand energy distribution. In Jupiter and Saturn, helium rain has been proposed to explain the excess internal heat. On Uranus, a similar process might cause heat stratification and hinder convection. While helium rain adds heat to the deeper layers, it might simultaneously obstruct outward heat flow. This dual effect could create a stable barrier within the mantle. The underlying mechanism involves phase separation in fluid mixtures under extreme conditions. As hydrogen and helium cool and mix, helium becomes incompatible with hydrogen under certain pressure and temperature conditions. It forms droplets that fall, much like the iron rain seen in Jupiter. These droplets coalesce, releasing gravitational energy as they sink. Detailed equations of STI are used to model this transition zone inside Uranus. This process may also affect the planet's magnetic field. Since Uranus's dynamo operates in a fluid shell, possibly composed of supercritical water or ionic fluids, any helium-rich layer could interrupt or redirect the flow. These disruptions could cause irregularities in the magnetic field, such as the large tilt and offset observed. Thus, helium rain might indirectly influence Uranus's magnetosphere. Although helium precipitation would not be directly visible, its effects could be detected through gravity and thermal measurements. Space missions that map internal density and heat flow could identify layering consistent with rain zones. Variations in thermal emissions across the surface might also reveal the presence of internal barriers. Coordinated modelling and observation are necessary to understand this process fully. Understanding helium precipitation helps in comparative planetology. It highlights a common feature of giant planet evolution, while also explaining why some planets behave differently thermally. Jupiter and Saturn show significant internal heat, partly due to helium precipitation, which releases heat outward. Uranus may operate differently, trapping or reflecting heat beneath its mantle. Laboratory and computational research continue to refine the phase diagram of hydrogen and helium mixtures under Uranus-like conditions. High-pressure experiments and quantum simulations are used to project the immiscibility threshold. Future experiments will validate whether helium droplets can form and fall under planetary conditions. The results will shape models of Uranus's interior. Uranus's helium rain hypothesis exemplifies the complex physics hidden within planetary mantles. It shows how microscopic phase behavior controls macroscopic properties like temperature, convection, and magnetism. This adds an extra layer of complexity to simple composition models. As missions and models improve, we may confirm whether Uranus indeed experiences helium precipitation. If so, it will shed light on why the planet remains thermally inactive. Uranus continues to be a planet of surprises, silent, invisible light but active in hidden processes beneath its surface. Jupiter extends its magnetic shield all the way to Saturn. Jupiter's magnetosphere is the largest of any planet in the solar system, stretching so far that its influence can reach hundreds of millions of kilometers, potentially even to Saturn. The planet's powerful magnetic field, fueled by its metallic hydrogen core, traps charged particles in an enormous cavity. As solar wind presses against the magnetosphere, a bow shock and massive magneto-tail form. This tail stretches outward, interacting with solar wind and potentially affecting neighbouring planets. In this way, Jupiter creates a magnetic shield that extends far beyond its immediate vicinity. The energetic particles within Jupiter's magnetosphere, mainly electrons and ions, move along magnetic field lines. Some of these particles get injected into heliospheric currents that travel outward. While most dissipate before reaching Saturn, some traces of Jupiter's influence can be detected by spacecraft travelling through interplanetary space. These interactions alter the structure and dynamics of the local heliosphere. Essentially, Jupiter acts as a massive magnetic lighthouse within the solar system. Observations from spacecraft such as Pioneer, Voyager, and Cassini confirm that Jupiter's magnetodisk can interact with solar wind in ways that produce ripple effects. These ripples alter the magnetic environment and shift the dynamics of charged particles moving through space. Cassini recorded variations in particle flux consistent with this distant influence. Such encounters suggest that Jupiter's magnetic tail extends beyond Saturn's orbit during periods of heightened activity. This magnetotail is dynamic, shaped by solar wind pressure. It can stretch and contract over long distances, with its structure and composition changing over time. Magnetic reconnection may occur, releasing energy and reshaping magnetic field lines. These processes generate waves or instabilities that travel through interplanetary space. Any planet within this domain may experience subtle magnetic fluctuations originating from Jupiter's influence. Beyond magnetic fields, Jupiter's rotating magnetosphere also generates periodic pulsations. Its rapid spin, completing one rotation every 10 hours, causes waves and oscillations that propagate outward. These periodic variations can excite distant instruments like magnetometers on faraway spacecraft. Even when weakened, the signal remains detectable across vast distances. Jupiter's magnetosphere thus exerts both static and dynamic influence. Jupiter's magnetic field extends beyond its boundaries, influencing the atmospheres of other planets. Charged particles can impact these atmospheres, generating auroras or altering ionospheric conditions. While Saturn has its own strong magnetosphere, Jupiter's outer influence may affect particle flows in that region. This creates a subtle but measurable effect, akin to a tuning fork echoing through space. Scientists model these interactions using magneto-hydrodynamic simulations to trace the evolution of Jupiter's magneto-tail. Data from planetary missions and solar observations feed these models, revealing how the tail extends, interacts with planetary magnetospheres, and dissipates with distance. Understanding these interactions helps map interplanetary magnetic connectivity. Jupiter becomes a key architect in magnetospheric architecture. Even though distant, Jupiter's magnetic reach provides valuable insights for studies of exoplanets. In star systems with giant planets, similar magnetic lobes might extend to neighbouring worlds, affecting their habitability, atmospheric chemistry, or auroral activity on moons and planets. Jupiter shows us that planetary magnetism can extend far beyond a planet's physical confines. Its magnetic shield shapes the heliospheric environment, sending ripples across space. By doing so, Jupiter claims a domain of magnetic influence, affecting everything in its path. Some theories suggest that a small object might temporarily orbit Neptune, acting as a lost moon that was captured and later escaped. This could be due to Neptune's strong gravity and the presence of irregular objects near its orbit. Small objects passing close to Neptune can get trapped in unstable orbits, where they may stay for a few decades or centuries before being ejected. This shows that Neptune's moon system is constantly changing. Models indicate that objects from the Kuiper belt and centaurs can be temporarily captured by the Neptune. When these objects pass near the planet, they enter chaotic orbits influenced by Neptune's moons, tidal forces, and solar energy. These objects may behave like small moons for a while, but eventually interactions with Neptune's moons, such as Triton, will cause them to be expelled. As a result, Neptune can gain and lose small moons over time, though very few are ever detected. It is hard to observe these temporary moons because they are faint and far away. Only precise surveys can find them. However, if unusual behavior or sudden appearance-disappearance of small objects occurs, it may indicate a temporary capture. The physics of these temporary captures highlights the active nature of objects in the outer solar system. Neptune's gravity and the balance between solar and planetary forces create areas where objects can be captured. These events show that moon systems are not static but change over time. If a lost moon is indeed orbiting Neptune, its orbit would likely be unstable, crossing paths with other moons or rings, which could lead to interactions or collisions. Over time, these interactions would either eject the moon or help it settle into a stable orbit. Studying these temporary moons helps us understand how moons were captured in the early solar system. It may also explain how Neptune's largest moon, Triton, was formed. Several small objects may have interacted with Neptune before one was permanently captured. By observing these events today, we can learn about the past formation of Neptune's moon system. Future surveys could help detect transient moons around Neptune. These discoveries could provide valuable insight into how moons form and are ejected. Temporary moons are also seen in other planetary systems. Mars's moon Phobos and Jupiter's quasi-satellites show similar behavior, but Neptune's larger gravitational zone makes these events more common. Neptune's distance and faintness make it harder to detect these moons, but their presence is still significant. The possibility of lost moons highlights that Neptune's environment is still evolving, with moons appearing and disappearing. Neptune's satellite system is not fixed. It changes over time. Uranus occasionally experiences faint auroras despite its weak internal heat. These ultraviolet auroras, seen as faint glows near the magnetic poles, suggest that solar wind interacts with Uranus's magnetic field. Although these auroras are weaker than those on Jupiter or Saturn, they show that solar particles occasionally reach Uranus's upper atmosphere. When charged particles collide with atmospheric molecules, they produce ultraviolet light. This shows that even with little internal heat, solar energy can still drive external activity. Hubble and space telescopes first observed these auroras using ultraviolet filters. The detection required long exposures and sensitive instruments. The auroras appear as faint patches or arcs, rather than bright curtains like those on Earth. They change based on solar activity, magnetic field alignment, and the planet's rotation. Auroral events are more noticeable when solar wind is disturbed, such as during coronal mass ejections. Uranus's magnetic field is unusual, tilted about 59 degrees from its rotation axis and offset from the center. This tilt causes the magnetic poles to move across the planet's surface during each rotation, making the auroral zones shift dramatically and making detection unpredictable. The occasional auroral flashes suggest temporary solar wind coupling. These events show that even distant cold planets can interact with solar wind. Despite weak internal heat, Uranus's atmosphere can still respond to these external factors. Charged particles in the magnetosphere follow field lines into the poles, where they excite hydrogen and methane, producing ultraviolet light. The irregular nature of the auroras highlights how much this process depends on solar wind strength, field alignment, and atmospheric conductivity. The frequency and brightness of Uranus's auroras are much lower than those on Jupiter or Saturn, but studying them still provides valuable information. It helps us understand Uranus's magnetosphere, atmosphere, and magnetic structure. By comparing these auroras with those on other planets, scientists refine how solar wind interacts with different planetary conditions. Uranus provides an important reference point for understanding magnetospheres beyond our solar system. Auroras on Uranus are linked to solar activity cycles. During solar maximum, when solar wind pressure is high, auroras are more frequent. During solar minimum, auroras almost disappear. Monitoring Uranus over many years could reveal patterns tied to these solar cycles. These faint signals track how solar energy affects planets far from the Sun. Uranus's auroras also help scientists study magnetic environments on exoplanets. Planets with tilted or off-center magnetic fields may have similar transient auroral displays. Observing these events can help us predict atmospheric loss, auroral feeding, and electromagnetic shielding. Uranus serves as a case study for unusual magnetic geometries beyond our solar system. Future missions equipped with ultraviolet spectrometers and magnetometers could detect auroras on Uranus more regularly. Coordinated campaigns with solar wind monitors from Earth or other spacecraft could help predict when these interactions occur. Mapping Uranus's auroral patterns would help link its magnetic field to the atmospheric response, revealing if auroras change with magnetic field geometry. Though rare and faint, Uranus's auroras prove that solar wind can drive activity even on cold ice giants. They remind us that external energy sources can cause planetary responses even without internal heat. Jupiter may have once had a companion planet. Theoretical models suggest that, in the early solar system, Jupiter may have had a twin planet of similar size. This hypothetical planet formed in the same area, but was lost due to gravitational instability. The interactions between giant planets and the protoplanetary disk may have destabilized their orbits, leading to one planet being ejected or colliding. Jupiter survived, while its twin vanished. This idea comes from simulations of planetary formation and migration. These models show that when giant gas planets form close together, their orbits can become unstable, causing one planet to collide with another or be thrown into space. Jupiter's current solitary position suggests it may have lost its twin planet in this way. While no direct evidence exists, the layout of the solar system supports this theory. Jupiter's dominance may be the result of early planetary conflict. Further evidence comes from comparisons with exoplanet systems, many of which feature a single giant planet, despite the expectation of multiple giants. This supports the idea that companions can be ejected, leaving behind one lone planet. Jupiter's current neighbourhood, which includes Saturn, Uranus and Neptune, suggests a dynamic past. Jupiter's gravity likely shaped the orbits of these planets after it shed its twin. Evidence of this can be seen in asteroid and comet behaviour in the outer solar system. The distribution of resonances and scattered objects in the belt may reflect the past scattering of giant planets. Ejected planets could have disturbed smaller objects, pushing them into distant orbits or causing collisions. These subtle effects are consistent with the long-term gravitational shuffle in the solar system. Jupiter's current position and mass indicate that it is the survivor of a tumultuous formation process. If Jupiter had a companion that was ejected, it would have carried away significant mass and angular momentum. This gravitational slingshot could have sent it far into the galaxy, unbound from our Sun. Rogue planets like this have been discovered, and one may be our missing companion, drifting through space. While it hasn't been found yet, it could still be moving through the interstellar medium. Its origin in our system would remain hidden, unless we trace its trajectory or isotopic signatures, a difficult task. Alternatively, the twin planet could have collided with another planet. While a collision of two gas giants is rare, it's not impossible in a dense early solar system. Such a collision would create massive debris and could result in heavy elements being produced in Jupiter's atmosphere. Searching for unusual core composition or strange internal structures could reveal clues about ancient impacts. Jupiter's core and composition continue to be important areas of study. Simulations of planet formation include the idea that multiple giant planets might have existed, creating a system similar to ours. If one planet is removed, the simulations show that the current orbits, asteroid belt and Kuiper belt structure would match what we see today. Removing this companion planet explains Jupiter's position and its stabilizing effect. This theory helps us understand how our solar system formed. The idea that Jupiter had a companion planet adds context to the early history of the solar system, showing that planetary systems can change dramatically over time. Jupiter's size and position today reflect that it is the survivor of this early phase. This theory has encouraged scientists to search for evidence in observations and models. It is possible that our solar system has been shaped by a lost giant planet. Learning about Jupiter's possible twin increases our understanding of the solar system's early instability. Jupiter's influence still shapes the stability of the inner planets. By seeing Jupiter as a survivor of a more crowded past, we learn about planetary system dynamics and the importance of early changes. Jupiter's dominance today is the result not just of its formation, but of survival and adaptation. The next topic focuses on Saturn's atmospheric patterns, which resemble those on Earth. Saturn has large planet-wide waves in its clouds called Kelvin waves, which are created by atmospheric currents near the equator. These waves are similar to what we see on Earth, but much larger. They move east and west across Saturn's atmosphere and change the height and brightness of the clouds. These waves show how Saturn's rotation interacts with its atmosphere and how energy is transferred through the planet's atmosphere. These Kelvin waves on Saturn are driven by solar heating and internal convection. They form horizontal waves that are trapped at the equator and carry energy without moving mass vertically. The waves on Saturn have much longer wavelengths and slower frequencies than the waves we see on Earth. Cassini's infrared and visible cameras detected changes in brightness and cloud spacing near Saturn's equator, which match the expected behavior of Kelvin waves. The waves influence Saturn's wind patterns and storm behavior. They can make winds stronger or weaker, depending on where the waves meet existing jet streams. These waves also affect how clouds form and how temperature is distributed across the planet. The wave patterns help us understand how Saturn's atmosphere works and how its weather changes over time. The source of these waves could be solar heating, convection, or interactions with deeper layers of Saturn's atmosphere. Saturn's internal heat might also be contributing to the waves by releasing energy. These Kelvin waves also help scientists understand Saturn's atmospheric stability and temperature profiles. Studying the wave properties provides clues about Saturn's internal structure and atmospheric stratification. Similar waves have been seen on other gas giants like Jupiter, showing that these wave patterns are common in rapidly rotating planets. The waves on Saturn are different from Jupiter's due to Saturn's slower rotation and colder atmosphere. Understanding these waves helps scientists model Saturn's weather and how its clouds behave. It also shows how equatorial oscillations transfer energy and affect storm systems on Saturn. Meteorologists now include Kelvin wave dynamics in their models to better predict cloud behavior and long-term changes in Saturn's atmosphere. Saturn's Kelvin waves are a subtle but important pattern in its atmosphere, like the heartbeat of the planet. They remind us that even giant planets follow physical principles we see on Earth, just on a much larger scale. The next topic may explore another type of atmospheric wave or return to the magnetic phenomena on other planets. Neptune has dark spots, which are high-pressure cyclonic systems. These spots absorb bright clouds and appear as deep blue-black areas on the planet's surface. These systems form, evolve, and eventually disappear over several years. Their darkness comes from the depletion of methane clouds above and the deeper absorption of atmospheric gases. These dark spots reveal Neptune's dynamic weather, which is hidden beneath a calm surface. One of the famous dark spots was discovered by Voyager 2 in 1989, but it vanished within a few years, only to be replaced by new ones in different locations. This shows that Neptune's atmosphere is constantly changing. Later, Hubble spotted multiple dark vortices at different latitudes, each with unique behaviors. Some spots move toward the equator before disappearing. These observations show that dark spots are part of a continuous weather cycle on Neptune, not just random events. The dark spots contain active wind systems with clear centers and bright methane clouds around the edges. Their circulation patterns are different from the low-pressure storms on Earth. These dark spots are deep cyclones that reach into Neptune's lower atmosphere. Their edges often have bright clouds that form because of upwelling and condensation at cold cloud tops. This contrast between the dark centers and the bright edges is what makes the spots so noticeable. Spectroscopy shows that the dark spots are colder at the cloud tops compared to the surrounding areas, indicating deep vertical flows of gases. The cold centers absorb little sunlight, making them darker. The surrounding methane clouds reflect light, creating a striking visual contrast. This thermal pattern helps scientists understand how deep the spots go and how energy moves through Neptune's atmosphere. Dark spots are like windows into Neptune's atmospheric layers and the movement of gases. These cyclonic systems share similarities with storms on Jupiter and the Earth, but Neptune's dark spots are driven by deep internal heat and fast winds. The formation of these spots might involve baroclinic instability or deep convection. Their lifespans and movements show how Neptune's atmosphere balances energy and dissipates it over time. Understanding these spots helps scientists model how the atmosphere of icy giants works. In some cases, pairs of dark spots interact, merge, or push each other away. Their movement across latitude shows how different parts of Neptune's atmosphere rotate at different speeds. Studying how these spots move over time helps us understand Neptune's wind patterns, jet strength, and how the atmosphere is structured. The presence of these dark spots challenges the idea that Neptune is a calm, inactive planet. Instead, it shows that Neptune has an active and complex atmosphere with deep storms and high-altitude methane clouds. Neptune is more dynamic than it seems. Modern telescopes continue to monitor how these dark spots evolve, confirming that Neptune's atmosphere is constantly changing. Simulations of Neptune's atmosphere help explain how these spots form and move when heat and wind shear are factored in. These models predict how long the spots last and how they migrate across the planet. Observing these spots helps us understand how Neptune's atmosphere works and how energy is distributed within it. At lower cloud-forming altitudes, one pattern emerges, whereas in warmer and deeper layers, another appears. Monitoring these distinctions is crucial for estimating temperature gradients at varying altitudes. These gradients play a significant role in determining wind speed through the balance of thermal winds. Data reveals that Uranus maintains a structured zonal wind system, powered in part by internal heating and in part by solar input. Unlike Jupiter and Saturn, the thermal bands of Uranus are subtle and require delicate infrared imaging to detect. Yet their persistence over the time indicates that these streams are stable and planetary in scale. While the jets themselves may be weak, they are organized into consistent belts, offering a rare look into climate dynamics on a planet with minimal solar energy and low internal heat. Uranus stands as a model for cold planet meteorology. The appearance of these climate bands also highlights the impact of telescope advancements on our understanding of planetary systems. What once seemed like a featureless planet now reveals intricate atmospheric behaviors. Infrared technology has shifted Uranus's reputation from dormant to moderately active, sparking renewed interest in atmospheric monitoring of ice planets. The band's visibility provides valuable evidence of the planet's climate cycles. The movement of these bands correlates with Uranus's extraordinary axial tilt and long seasons. As sunlight shifts between the hemispheres, temperature disparities change, prompting the bands to adjust. Variations in the amplitude and positioning of these bands support the idea of seasonal modulation. Although modest, these alterations confirm the interaction between solar energy and the planet's internal structure. While Uranus's weather may seem slow, it is far from stagnant. These climate bands help fine-tune models of atmospheric circulation, specifically for ice giants. Accurate predictions of wind speeds, convective layers, and heat distribution must factor in the observed thermal patterns. The models that best replicate these bands also forecast potential storms or cloud events, which can be tested through observation, creating a feedback loop that connects measurement and theory. Studying Uranus's climate bands could offer insight into exoplanets with similar characteristics. Many exoplanets are cold with slow rotation and minimal stellar energy. If these planets have zonal flows, they may exhibit detectable thermal bands through infrared imaging. Uranus serves as a case study for understanding the climates of these exoplanets, helping us contextualize climate physics beyond our solar system. The thermal bands of Uranus prove that even faint and distant worlds can have structured weather. They remind us that the depth of observation makes a difference. What might be invisible in one spectrum could be clear in another. The thermal stripes on Uranus are a testament to atmospheric circulation under weak external forces. Moving forward, the next topic will explore either ice planet phenomena further, or delve into surface or interior anomalies. Jupiter has a subtle yet significant influence on Earth's axial tilt across millennia. Jupiter's massive gravitational pull has an ongoing effect on the orientation of Earth's rotational axis, altering its tilt by a fraction of a degree over millions of years. Although small, these changes are climatically important. Jupiter's interaction with other planets causes slow shifts in Earth's orbital parameters, which are part of the Milankovitch cycles and influence ice ages on Earth. Jupiter thus plays an indirect role in stabilizing Earth's long-term climate. The gravitational interactions that occur involve complex resonance patterns among the planets. Jupiter's nearly 12-year orbital cycle results in periodic gravitational nudges to Earth's tilt. Although Venus and Saturn also affect Earth, Jupiter's influence is dominant due to its immense size. Over hundreds of thousands of years, these combined forces create oscillations in Earth's axial tilt, shifting it by about plus or minus 1.3 degrees. This plays a role in regulating ice accumulation and melting cycles. Models of Earth's axial tilt evolution indicate that without Jupiter, Earth's tilt would experience much more chaotic and dramatic changes. Research suggests that a planet of Jupiter's size helps reduce extreme tilt fluctuations, reinforcing orbital resonances and limiting unpredictability. Jupiter's presence helps keep Earth's climate stable, avoiding extreme seasonal swings. Without Jupiter, Earth would likely experience far more extreme climate fluctuations. Evidence supporting Jupiter's influence comes from paleoclimate data and simulations of Earth's orbital history. Ice core samples and sediment records show periodic glacial cycles that correspond to changes in Earth's axial tilt, with patterns aligned with Jupiter's orbital period. By correlating climate data with gravitational models, scientists have shown that Jupiter's presence is evident in Earth's geological history. Even though Earth's axial tilt changes slowly, even minor shifts influence the amount of solar radiation reaching the poles. These shifts impact polar ice, ocean currents, and atmospheric circulation, which in turn affects sea levels and biodiversity. Jupiter's gravitational pull has thus played a critical role in shaping Earth's climate, not through direct interaction, but through gradual celestial movements. Jupiter's impact also extends to Earth's tilt through interactions with Saturn. The gravitational relationship between these two gas giants influences Earth's axial tilt and contributes to long-term climate stability. Without this interaction, Earth's orbital history would have evolved in a very different way. Although Jupiter's influence on Earth's axial tilt is modest, it has profound climatic consequences, especially when seen over extended cycles. Larger ice ages occur when Earth's tilt is at its peak, while warmer periods align with lower tilt angles. Jupiter's gravitational signature is imprinted on Earth's habitability, acting as a subtle but crucial participant in Earth's climate system. Recognizing this influence deepens our understanding of planetary interactions and demonstrates how distant giants can shape the conditions of inner, habitable worlds.